Hello, everybody. Let's just wait a little bit more minutes and for other people to join. After that, we will have a quick revision of the first and the second lecture, and then I will open up the quiz so that you get at least a very good grade on this one, right? By the way, how are things going with your projects? So are you guys starting to think about them and get some ideas?
Could you tell us about today's activity about projects?
Yeah, we will have a discussion about each individual project after the lab. So basically, yeah, after the second session, or probably the third session, right? Science. This is looking a bit better. Now let's move this to the right. Move this to the right. There we go. Can you guys see my screen now?
Yes.
Nice. So let's just start with a quick revision for the first lecture for the classification lecture, and just tell me, guys, what do you remember from that one?
Lime and Gradcam. Oh, first lecture. Okay, sorry.
Yeah, the first lecture. So what did we speak about? We started speaking about general things such as linear regression, logistic regression, what is supervised learning, unsupervised learning, classification, regression. And then we went on and started building like this on top of it. Yeah. So what do you guys remember?
I remember we spoke about convolution, but it was at the end.
Yes, so we spoke about convolutional neural networks. In the
Yeah.
end, in the start, we spoke about linear regression, and then we saw how linear regression can be mapped into logistic regression. And then from logistic regression, we started speaking about things like what? Neurons and perceptron in general, or more specific. And then we spoke about multi-layer perceptron. So can somebody try to remind me of what was the line of thought that we used here, like the comparison that we used between multi-layer perceptrons and linear regression, right? So just for like a quick reminder, what we said was linear regression, even if it's a very simple model, it's able to map different concepts to each other, right? So we took the example of mapping the weight of a person to his height. And we did that using just a very simple linear model, linear formula. We mapped this one into logistic regression where the concepts don't really need to be full numbers. They can be like concepts such as classes, right? So categories and classes like that. And then we saw that a neuron, in fact, it's just a logistic regression. And the logical idea of mapping a bigger concept to a concept to another was to introduce multi-layer perceptrons. So basically we add multiple sequential, let's say, logistic regressions after each other. And instead of having just one logistic regression or one concept mapping at each level, we decided to have multiple logistic regressions at each steps. And this gives us different layers. And each layer is a set of logistic regressions. In other words, a set of concept mappings, right? So we're mapping the input concepts into something, into other concepts a bit more abstract. And then we repeat this, we map those abstract concepts into things that are even more abstract, and so on and so forth, until we reach the final layer for classification, where we're able to extract much more deeper information. Now, for CNNs, we spoke about what convolutional operation is. So the convolutional operation. Now, can somebody tell me what is the equivalent of a neuron for CNN, right? So what is a neuron in the CNN?
Logistic regression.
No, in the CNN. So how do you see a neuron in CNN? This is a very good question. Try to think of it slowly. So a neuron is just a logistic regression, right? So it's just a set of weights that will be multiplied by the input and then summed together to give us an output. So what are these set of weights that represent one single neuron in the
Kernel?
network? Can you repeat that?
Is it a kernel? Like, yes.
Yep. Kernel or a filter, same name. Nice. So a kernel and a filter represent a neuron or represent basically a single logistic regression, or represent one concept mapper. Another way to think about it, one concept finder, right? So it's trying to look for a certain concept. So this is, I think this is more clear for the students who took the introduction to computer vision, and they have seen that the different convolutional filters are in fact just trying to find a certain pattern in the data, such as, for example, certain types of edges or certain types of corners. And this is exactly what is happening here. So convolutional filters are very similar to neurons, in fact, so they're just the same thing. They're also a logistic regression, but the main difference between a kernel and a neuron has just one output value, right? But a kernel has, let's, I don't know, how do we write this one? Like this? No, let's put it like this one. Yeah, kernel outputs a concept map, right? So in the case of fully connected neural networks, what we do is we take the input and we try, if we find a certain concept in that input, we will fire an activation, right? So our activation function will be above a certain threshold, and we will be firing a certain activation. Whereas for kernels, what they will be doing is they will be searching for, so it's the same thing, right? So they will look at a certain part in the image. If they find the concept they are looking for, they will fire an activation. If they don't, they will not fire an activation, but their output can be looked at as a map of activations, right? So this is why it's called the activation map or the feature map, right? So this is the output of one single kernel, one single filter, or one single neuron in the CNN will not be just one value, but will be a map of values that would tell you if the concept the neuron is looking for exists in that area. So remember just this concept of an activation map. Oh, it did not work. Oh, nice. After that, we spoke about the different, so basically things such as, or let's call them tips for neural networks, which are, what are they called? Pooling. So we have seen max pooling. They say it's the best for now. We have seen other things such as padding and stride. Now, can somebody say a quick word about, for example, stride?
It is how much you move your kernel, maybe by one step or two steps, it depends, by 1 pixel or 2 pixels.
Perfect. So this is just the step size, correct. Can somebody say something about padding? Why is it used? What it is and why is it used?
If we don't use it, we might lose like values on the edges of an image, for example.
Uh-huh. And another one. So the size of the CNN, remember, the size of the input of a convolutional layer and the size of the output of a convolutional layer. What is the relationship between them, typically without padding?
If we want to keep it the same size.
Yes, increase the size of the output, meaning we can, we can afford to stack multiple layers of multiple convolutional layers after each other, leading to better abstractions and more in-depth understanding of the classes and the images we're working with. Where on the other side, when we don't use padding, just stacking 10, for example, convolutional layers, you're going to end up with 0, right? So you're just the image size of the output of the last one will be super small, that you would just tend to remove a lot of the information from the image. So what is pooling? So why do we use pooling?
Focus only on the, like max pooling, to focus only on the important information, for example.
Yes, focus only on the, let's say, larger concepts, the biggest activations. So remember this concept of each neuron will fire their own, well, let's say concept map, right? So for example, in the place of the nose looking, the kernel that is looking for a nose will fire an activation, but everywhere else, there will be no firing. Now, what helps us with pooling is it will shrink basically the size of the image. And in this case, we will be able to find or to focus more on the location of the nose without having to look through it in a very, very large activation function. Now, another problem with this one is once we merge, for example, 4 or let's say 8 different pixels together, we might lose the source of the information, right? So was it in pixel 1 or was it in pixel number 9? So this is one problem that arises from pooling. But since we do not really focus a lot on the location of the nose or the location of the activation, we just care if it exists or not. In that cases, pooling does help a lot because you're not really focusing on where was the activation located. Mainly you're focusing on whether there is an activation or not. So this is why max pooling works very well. So it reduces the number of overall parameters and makes the search much easier. So this is it for our first lecture on classification. So let's just call this one classification, lecture 1. And I will send you guys an image of this beautiful chart right now. Next, we will do another beautiful chart for interpretation. Yeah. Now let's make our second chart. Mind map. So for now, let's go to the second lecture. In the second lecture, we spoke mainly about interpretability. We started by speaking about what is interpretability, why is it important, why should we even care about it, what are the different scopes or types of interpretability, and then we spoke about what are the easily interpretable models, and from there we spoke about LIME as a black box object detector, and then we spoke about GradCam. So can somebody throw around the things that they remember from the last lecture? So what do you remember, for example, about the different or interpretability? Why? Why do we use interpretability? Why is it important?
To know why our model gave results it gave. Like, for example, it's important for medical stuff, for cancer prediction or something like that.
Understanding the models, and especially in critical application domains, such as medical cases. Other things could be like satisfying, as we said, human curiosity. Another reason could be safety measures, right? So just as you have said. And another one could be in here, for example, trusting or deciding whether to trust the model. So basically, we could try to use this in the following setting, right? So we have a model, and the model tells us we have 99% accuracy and patata patata. But instead of just focusing on the number of 99% accuracy, we could try to look at the most challenging situations and have a panel of experts that would analyze whether the model is actually looking at the right stuff in these cases. And so just another way to say this could be to debug the model or to audit the model. Next, let's start speaking about the scopes of interpretability. I hope you guys remember the 5 scopes. So I know you all remember the last 2 scopes, but let's see who remembers the first 3, right? So there are 5 of them. Who remembers the first 3 scopes?
Knowing how it's trained.
Yes, the training function. Let's just say train. The second one.
Prediction.
The predict function. Nice. And the third one?
Features that contribute to the result.
Yes, so let's say component contribution. Last 2, that this is easy, right? So I'm sure everybody remembers this. Who can choose?
Yeah, how decision is made for a single item and how decision is made for group of items.
So single instance and groups of instances. The majority of the research is being done on this one, but if some of you guys would like to work on groups of instances, this is also a very active area of research, or a very important area of research. It's not very active, but it's very important. Now, can you tell me what are the 2 most interpretable models that we have seen so far?
Logistic regression and
Logistic regression.
Decision tree.
And a decision tree. So without going into a lot of details, can somebody tell me how would you interpret logistic regression's weights, for example, in terms of what are the most important features or what are not the most important features?
You spoke about something like creating a smaller model.
No, yeah. I mean, what I'm saying is, I'm speaking about the 3rd level of interpretability, right? So can somebody tell me how would you evaluate or understand the weights of the logistic regression, right? So not the weights, but let's call them the A and B, right? How would you interpret A1, A2, and 3 in terms of which feature is the most important and which features are the least important?
Yeah, for example, the coefficients, whichever is higher.
Yes.
Yeah.
So highest coefficients have highest importance features. Low coefficients have low importance features. Now, can somebody tell me for a single instance, let's say, for example, let's call this, I don't know, yeah, probability, safety probability, right? Let's go, safety probability. So this is the probability that the person is safe to make a loan for. Let's say it's equal to 100. 100 is the B, plus 5 times income minus 10 times original debt, right? So if somebody comes to you as one person, as a single instance, and they have a value for income and a value for debt, and we refuse them, how could you tell them, or what would you tell them to change in order to, how would you do this interpretability of the model, saying that he should change, right?
They'll just tell them to increase their income and decrease their debt.
Exactly, this is perfect. So as you have seen, interpreting logistic regression is a piece of cake, so it's easy and everybody can do it. Now let's go to decision trees. How do you explain on a single instance?
We can just follow the branches until the leads.
Exactly.
See how an instance is classified.
Follow the branches if conditions towards the leaf. Nice. And how do you change? Sorry.
It basically change the path to another leaf that is that is intended.
To a different leaf, right? Perfect. Now let's go to the real deal, right? So let's speak about Lime. So first, can you apply Lime to only one type of data, or is Lime applied to one type of model? Is it so? All of these questions. What do you guys think?
To any model?
Yes.
It's a black box, so it doesn't make any assumptions.
Exactly. So black box meaning any model works with all models. Next, type of data that it works with.
Images,
What else?
text, not sure.
What else? The most basic type of data? CSV data, right? So tabular. Yes. Now, just like a simple revision about it, can you tell me what it does? So just the basic idea is to train a local linear model to estimate the non-linear model's decision, right? So basically what the assumption is, this is something that is highly non-linear, but if you zoom in, for example, at this point, if you zoom in very, very much, the decision in this area alone becomes a linear decision, right? So basically what we're saying is, doesn't matter how non-linear the model is, if you zoom in, sorry guys, if you zoom in closer to its decision boundaries, it will always be something close to linear or something estimatable by a linear model. So this is where the idea came from. So basically what we do is we will train a linear model or weighted linear model on local area. So basically for a selected instance, for the instance of interest, to estimate where basically the bigger non-linear model's decision, but only on a local place. And now let's go, just small question. How do we make the work on images and texts? So how do we apply it, for example, to text data? What needs to change in the algorithm to be applied to text data? Well, to go easy, we need to add a conversion function from text into a vector and from a vector into a text, because the algorithm for Lime by default only works with CSV data or tabular data. So what we need to do is to convert our text into a vector. Very easily, we just convert it into a 1, 1, 1, 1, 1, 1, 1, 1 vector. And then we just generate random vectors where some of these values are set to 0. And the values which are set to zeros, we just ignore the word on that index. Same thing for images. We convert it first, we superpixel the image, meaning we split the image into different regions. And then each region will be either turned on or turned off while we send them to our original model, see their predictions, and then basically build our data set for building or training the local nonlinear model or weighted linear model. Next is GradCam. So GradCam, as we saw, has two main aspects. The first aspect is it will try to understand or estimate the important features that the model is looking at. So first thing is it will try to understand what is important for the model in general, and then we focus only on what is important for a chosen class. So how do we first find the important features in general? Usually we do this by looking at the last or pre-last, let's call them last plus minus, right? So the ones in the final layers, CNN maps. This map will allow us to look at what are the concepts that the model is looking at. So what are the concepts that the model has extracted from the image? And then if we would like to focus only on a certain class, what we do is we take the gradient of the class with regards to the feature maps. And then we combine basically the different feature maps based on this weight, which is basically just the average of the gradient. And ta-da, there we go. We have this beautiful mind map. Now I'm gonna send you guys this mind map again. Hopefully now with the revision, all these concepts will be kind of stored for a longer period in your brains. And we will start the exam pretty soon. Does anybody have any questions about the previous two lectures? Nothing? Nice. Interpret the T. So let me send these two. Nice. So can somebody tell me, should we start the quiz right now, or should I give you guys a bit more time to look at your slides or to your look at your lecture notes?
No.
No, so let's go for it. I think the quiz is already open, so you cannot see it. So let me just make you guys able to see it. Nice. So now you should be able to see the quiz. Go ahead. You can start at any time you want. The quiz is not like bound to a certain hour, but it is bound with a certain time limit. So once you start, you only have 10 minutes to finish. You have access to all your lecture slides. You have access to all the internet you can find in the world, but you do not have access to discuss answers with your friends. So try to work on it separately. This is mainly just for self-evaluation, just to make sure that you guys understood very well the concepts that we covered. So good luck, guys.
Excuse me, can I ask you a question?
Yeah, go ahead.
The convolution question about the size of the output feature map.
Yes.
We
Yeah.
only use one kernel?
That's a good question. Let me just check it out because that's actually the trick in the question. So let me check it out. What is the width of the feature map? Right. So the width, it's not really. So you're speaking about this one, like the width of the feature map? Question number 6. Yeah, question number 6. I think it's regardless of the number of.
Okay, only the width.
Yeah, just the width, right? Or the height. So it's the same number, right? So yeah.
Okay.
Yep. A good question, actually. It will be a good question once you go for the exam, because the exam has a trick question about that. I think there was also an error. Yeah, question number 7. Yeah, question number 7 certainly has an error. Yes, so only a simple model trained on the training data. So all the others is just an error in copying. A simple model trained on the training data. Yes, exactly. Question number 8. Yes, each class or each class separately. This is correct. 9, correct. Okay, things are looking good.
About question 5, do we care about channels?
As I said, let me check. Pooling layer with the same stride convolutional size. Really doesn't matter if you think about channel wise or not channel wise. What I'm speaking about in here is whether the width and the height will be the same.
Okay, cool. Thanks.
Yeah, but yeah, regardless, it's gonna be the same answer, right? I think the majority of you has already finished and only a few ones are left. So take your time again, don't worry. And for the majority of the grades, they're looking very good. Can you guys see the grades already, or you can't see them?
No, we can't.
Okay, that's nice. So the average grade so far is 9.7. So that's very good, right? Nice. So everybody has finished now. How was the quiz? Was it too difficult? Was it too hard? Was it too easy? Was it too fast? Too slow?
I think it was okay.
Yeah,
was,
agreed.
yeah. I think it was too easy even, right? So next quizzes will be much harder than this one. So this was just to give you guys some good grades. So I'm gonna release the grades for everybody. And can you guys now see your grades?
Yes.
Yeah. Perfect. Nice. So let's take a quick 10 minutes break, and we'll come back again for the next lecture, which is the lecture on object detection. This lecture will be exactly similar to the lecture previously made in the Introduction to Computer Vision course, but this one will contain a bit more information about things such as mean average precision and some different activation functions such as MISH and SWISH and all of these beautiful names. After that, we will have our lab. The lab for this case will be a bit more advanced. So we will have 3 labs. Basically, we will have a lab on faster RCNN, a lab on YOLO v4, and a lab on YOLO v5. And we will see that all of them are actually very easy and very basic. We will just take a look on how to train all of these different models. And if you guys need a bit more time, we could spend, instead of just 1 hour and a half, we spend a bit more on each one of these different models. And hopefully on the next lecture, we will start with the natural language processing part of the course. And yeah, so see you guys in 10 minutes.
Excuse me, I have a question.
Yeah.
Like in the 9th question, it's written GradCam
Yes.
is just a weighted sum of the feature maps with the ReLU.
Yeah.
But it's not just a weighted sum of the feature maps. You have, I mean, we have first to calculate the alphas by averaging the gradients.
It's just a weighted sum, right? So you're just going to have to calculate the weights.
But not of the feature maps exactly, directly, I mean.
Let's see.
The weighted sum of the feature map activations were the weighted.
Let's take a look at it, right? So let's look at the images again. And it's good to spike these discussions, because this is what learning is, right? So basically finding out when there are some, yeah. Let's see. So here you can see, so what we are doing is just taking the convolutional feature maps. So these are the activation maps or the convolutional feature maps, and we just sum them up pixel by pixel using different weights. The weights, of course, this is just the average of the gradients of the class probability with regards to the feature maps. But again, it's just a weight. So it's not really something very influential, right? So it's just a weighting function. The most important part is the convolutional feature maps, right? So basically, we're just doing a summation over the convolutional feature maps, and then we send them through the ReLU to make sure there are no negative values. So even the ReLU is something that is not very important for the model, right? So the most important part is that it's looking at the convolutional feature maps.
Yeah, I see now. Thanks.
Nice. So it's just, I mean, the essence of GradCam is a very simple idea. See you guys in 10 minutes. And just to put it in numbers, I think it's 33. Guys, I hope you guys are back. So as we said, now we're going to start our object detection lecture. Just to make sure, do you guys have any other questions concerning the course? Anything else before we start? Sounds good. So for today's lecture, we're going to speak about object detection and object detection models. So this was already covered during the introduction to computer vision course. So the majority of the data scientists already know these models, but as promised, we're going to cover a bit more. So we're going to see things that we have not seen in the introduction and hopefully learn those things that we have seen before, but learn them in a bit more in depth. So the learning outcomes of this lecture are to understand what is object detection and speak about the most basic algorithm, which is the RCNN algorithm, and then try to see what are its, well, how do we say this? Successive versions. So the fast and faster RCNN, which are a bit much, so better in terms of speed and of course, better in terms of performance. And lastly, we will speak about YOLO and detectron, which are the two most commonly used words in the field. And of course, there are the other types of models which are based on attention. And these models will be covered hopefully in like 3 weeks, right? So basically next week, we will speak about natural language processing in general. And after that, we will speak about attention in natural language processing. And after that, we will speak about attention in computer vision and namely in object detection. So speaking about object detection, let's start with the differences between traditional image classification and object detection. So for image classification, what we are trying to do is we take an image and we attribute a single label to this complete image, right? So this is a cat. Of course, this is not very useful in most cases because, for example, in this case, we can clearly see that there are other things besides the cat, such as the grass, such as, I don't know, other things, right? But for object detection, now we're trying to basically locate where the cat is inside the image, right? So instead of saying there is just a cat, a dog, and a duck somewhere inside this big image, we now try to pinpoint the exact location of these different objects. So for example, this is cat number 1, this is cat number 2, this is a duck, and this is our beautiful dog. Its applications are quite endless. So we can take, for example, something such as vehicle counting. Let's zoom this a bit more. So this is an algorithm, or this is an application that can be used by any of our practical developers. So the people who are trying to use this course as a practical course. So basically, simply you need to combine two things, which are object detection and object tracking. So just keep in mind this car number 9, for example, car number 9, car number 9, car number 9, car number 9. So the challenging part in here, or the thing that we have not seen yet, is not the detection of the car, because the detection of the car is pretty simple. This is a car, this is a car, but making sure that we keep track of, this is car number 17, it started in this area, and throughout the whole video, we make sure that this car number 17 is still labeled as car number 17. So this helps us for things such as counting, such as tracing, tracking, and all of these things, right? So for example, what we do is we take car number 16 in this case, we are following it while it is walking through the highway. Once it crosses this threshold that we manually set, so this line, we just increment the input counter. If a car comes from this side and walks in this direction and crosses this threshold, we increment the output threshold. You see? The algorithm is not perfect, certainly, but it's still doing a relatively acceptable job, mainly for multiple reasons. It's only using YOLO v3, so it's not like the best state-of-the-art model, And of course, even the object tracking part is a bit lacking, but still, as a first try, this is really impressive. And it's very simple to do, right? So this is one idea for a project that people could take, not necessarily, well, what is it called? Not necessarily vehicle counting, but you could do something such as people counting, or well, something like that. Or let's say, I don't know, you guys still do the attendance in clubs and stuff like that, right? So if you go to, let's say, badminton club or something like this, usually there is like an attendance sheet. So maybe there could be something that counts how many students came to this club meeting today, and I don't know, find the student from the database, right? Or something like that, something easy, right? Another application could be facial detection and recognition. So the facial detection part is done using object detection because it's, again, a face. So the face is just an object, but the facial recognition, this is something that is done using different models. For those who have taken the course of Introduction to Computer Vision, we spoke about a very basic algorithm to do this task, but now let's start to speak about the good algorithm, right? So for this one, I think I might spend some time on it. Yeah, let's just draw it here. So it's a very simple and basic idea. Basically, this is your encoder, right? So I'm sure everybody knows what is an encoder. It's just a CNN that will extract a latent representation. This is Z. So what happens is, let's say person number one is, let's say, Ahmed. So we have Ahmed, right? We have some pictures of Ahmed. Let's call them picture 1, picture 2, and picture 3. What would this give us is Z1, 1, Z2, 1, and Z3, 1. So what does this mean? This is Z, meaning the latent space of image number 1 that belongs to Ahmed, image number 2 that belongs to Ahmed, image number 3 that belongs to Ahmed. Let's say there is another person such as Lev. And we also have different pictures for him. So we have Z1, 2, Z2, 2, and Z3, 2. So what this gives us is basically a list of different features, or yeah, this is just different points. Let's call them points in an n-dimensional space. And once a new image of a new person comes in, so let's call this person X. This person X must be someone in our data set. So what we simply do, we send it through the encoder. We have our ZX, and this ZX, we just compare it to each one of these. Just measure the distance or the difference between each one of these values. And whatever is the closest, this is the person that we're seeing. So if this ZX is similar to Z11, this person is Ahmed. If the ZX is similar to Z22, for example, this person is Lev. Now, of course, when we have a few people, it's very fast. When we have a lot of people, things get a little bit more difficult. But there are, again, lots of different algorithms that can help you with this one. So there are things such as, I don't know what are they called, but something based on trees, right? So just first start to check the difference between the first feature, and then it goes to the second feature, third feature, fourth feature. And this one just simplifies the calculations or speed up the calculations. It does reduce the accuracy, but it does speed up the calculations. Now, this is something that you guys should have studied in the course of advanced information retrieval or information retrieval course. Did you guys do this? No?
Could you repeat the question, please?
Did you guys do anything in information retrieval course that is related to facial recognition or improving the results of search algorithms?
Not an information retrieval course.
We did search algorithms, not basically, not people's stuff.
Okay, okay. So probably it's done in the advanced information retrieval course, because I remember we did take this. Sorry, guys, my voice is breaking. Another application of object detection could be something such as parking lot monitoring, which is what we will be doing in today's lab. So the application is pretty simple. So we basically just take we take an image and we try to find out what are the available slots in a parking lot. This one could be used, for example, in a smart parking monitor or something like that, right? In Innopolis, I think somebody could do something very similar to this one, just basically go to the highest floor in the university, take picture of that external parking lot and manually annotate it. And there you go, you have a parking lot monitor after you train a simple object detection model. So a very basic idea. So for those who already took the course, so you already know this model, but a very basic model that can do the task of object detection, which is something that I think any of us could think of. And it's basically sliding a 2D CNN model, right? Basically, you take a image classifier, right, for the classes that you want, and you just slide it through different parts of the image. And whenever the model tells you this is a high probability location, we take that as the location of the object. There's one big problem with this one, which is the speed, right? So the speed of this, meaning the stride that we use to walk through the image, is just very huge. This is very big number. So basically, let's say it's 1000 by 1000 pixels. So meaning we will move the image classifier, let's say 700 times, right? So moving it 700 times in this axis, moving it 700 times in this axis, 700 by 700. And each one of these steps, we're going to have to apply a full convolutional neural network, meaning it's going to take us like 0.5 seconds, for example. 0.5 seconds times 700 times 700. This becomes already too big, and the model that we propose becomes something very hard to do. But we can actually fix this problem using a simple pyramid trick, right? This pyramid trick is something that you will find basically everywhere in computer vision, where especially in the new articles, what we do is we try to go in the lower level representation of the image. So this one is the more condensed representation of the image. So the smallest shape, or like the smallest resize possible of the image that keeps basically the objects of interest. What we do is we slide through this image. Now, since this image is pretty small, we can slide our classifier through all of it, and it wouldn't take us 700 by 700 trials. Let's say it would take us 20 by 20. So it's already much better. And instead of going again through all of this bigger image, and sliding it pixel by pixel, we would focus only on the areas that had some high activation. So for example, in this location, in this smaller sized image, our object or our image classifier has detected something interesting in this region, right? Of course, the location will not be very precise because the image is much smaller. So what we do is we increase the image size and we only search in this location. So again, this area is much smaller than the whole original image. So it will be, instead of 700 by 700 pixels, we will just move in a location of 20 by 20 pixels. Once we do that, we would precise or find a better location of the object, so more precise location of the object, and then just increase the size of the image and start searching in this smaller region again and again. Once we do that, we find even like a more precise location in that region of interest, and we increase the image size again, search even deeper inside, increase the size of the image again, search even deeper inside. So as you see, it's a quite sequential model. Instead of doing it 700 by 700, let's say we do it 20 by 20, and we repeat it 5 or 6 scales. So it would be 20 by 20 by 5, which is much, much smaller than 700 by 700. Another idea that pops in mind is the selective search idea. So the selective search idea is a trick that speeds up basically the calculations or reduces the amount of calculations we do on the image. And it does that by following a simple clustering trick. So I asked a lot, and the majority of you have not taken in the machine learning class a clustering technique called mean shift, right? Or did you guys do it? Mean shift. Anybody knows what mean shift is? Maybe somebody has taken it before. Nope. So basically, mean shift is an algorithm that would combine different regions of the image. So take, for example, this one. It will segment the image into these different smaller regions, right? So it's very similar to superpixeling that we have seen before. It's one of the techniques that could be used for superpixeling, for example. And it's a very simple algorithm of clustering algorithm. What it does, basically, it starts at random points, takes a radius of interest. This radius of interest is a parameter that starts with the model, and then moves to the location of the mean of the points that are inside this region of interest, and then repeats this again and again until it finds the area with the highest concentration of mass, or the center of mass, basically, right? So it just continues repeating and repeating until the mean of the points inside the circle is exactly in the center of the circle. And then it repeats this in lots and lots of different places, and it would give you the different, let's call them modes, or different cluster centers, or centers of mass. And this technique can be, as I said, very useful for clustering things such as images or segmenting images. A very similar technique is being used for selective search. So the selective search algorithm is an algorithm that is similar to a clustering technique. What it does, it just combines the different pixels of the image based on things such as texture, the colors, the intensity, the brightness, and other factors. And what it does, for example, let's look at the front of this truck. So we see the front of the truck is red. What it will do is it will combine this red segment and propose it for the CNN as a potential location for an object. And then it will combine this back of the truck, the white back of the truck, together and propose it as a possible location for an object. And once it does this first level, what it will do is it will try to combine different regions, right? So as we said, the back of the bus is very similar to itself. This front of the truck is also very similar. Now we combine both the back and the front and propose this as a potential location of an object. And then it will repeat this step of again and again of combining connected regions or connected potential regions again and again until we have lots and lots of different proposals. It will be like time consuming. Usually it takes like 2 seconds to process one image, and it will give us something around like 2,000 different potential locations for an object. But again, 2,000 is a much smaller number, is a much smaller number than, say, 700 by 700, which is like, I don't know, 700 by 700. It's like a very big number, right? So selective search is, again, another idea to speed up or to improve the speed of our potential model, which is sliding A to DCNN. Now, the next step is to evaluate our model. Say that we have a potential object detection model. How do we know if it's a good model or it is a bad model? For image classification, we usually use things such as F1 score or such as what is it called? Accuracy or precision, recall, and things like that. In object detection, we use one very important metric, which is intersection over union. And we use another very important metric, which is very similar to F1 score. And this one is called mean average precision, right? So you can already guess that it contains the precision, which is one of the components of F1 score. And the average precision is just a weighted average, and the weighted average is the change in the recall. So basically, mean average precision is just a way of combining precision and recall in order to give us a metric, right? So it's very similar to, as we said, F1 scores or the area under the curve. We will speak about mean average precision after this lecture, but for now we will speak about the intersection over union, which is the simplest form of evaluating object detection models. What it will do is it will, as its name suggests, calculate the intersection between a predicted bounding box and the real bounding box, and then divide it by their union. So if we would like to study this a bit further, what we have is intersection is a very interesting concept, which is always bigger than or equal to 0, and it's always smaller or equal to the union. Meaning intersection over union is always a number that is between 0 and 1. And between 0 and 1, this means it's a very good metric for evaluation, because we know 0 is very bad, 1 is very good. For example, if somebody says it's 0.96, this is also very good number. So it's a number that is very humanly interpretable because it's always bounded between 0 and 1. And the best case is when intersection is equal to the union. Basically, it's a full overlap of bounding boxes. This metric is used in two ways. First way is to check the differences between predicted and real bounding boxes. And another one is to check the differences between a predicted bounding box and a predicted bounding box, right? So one would say, why would you check the difference between a predicted bounding box and another predicted bounding box? And this is why we use for non-maximum suppression. So non-maximum suppression is a very important algorithm that is usually performed on all the different models that we currently are using as state of the art. And non-maximum suppression has the following idea, right? So let's say our sliding 2D CNN. So we're sliding it through this image, and it launched an activation for the object in this region. And then we slide it a bit more, and it launched an activation here. And we launched it a bit more, a bit more, a bit more. And here it also found an object. So you can already see by visually that these three bounding boxes are all predictions for the same real object. So what we do is, using non-maximum suppression, we would kind of basically combine all of these three bounding boxes in only one value, right? So we're trying to find what is the value that is the most maximum or the most trustworthy bounding box in this region. How do we do that? Simply by calculating a measure of similarity between the bounding boxes. We can all see that this bounding box is very close to this bounding box, which is very close to this bounding box. Meaning, if we just use the intersection over union metric, it will be very high between this one and this one, and it will also be very high between this one and this one. What does that mean? If there are bounding boxes in our predictions which have high overlap over union or have high intersection over union between each other, we remove the one with the lowest probability. Remember, CNNs, they don't just give you the class, they give you the probability of the object or the image belonging to a certain class, meaning we can easily compare which one of these two or which one of these three bounding boxes has the highest probability of being the object, and we just remove all those which have a low probability, and we keep only the bounding box which has the highest probability. To put this in algorithmic terms, so first we select the proposal with the highest confidence score. A confidence score is basically what you get from the output of the CNN in the case of our sliding CNN model. And in other models such as, let's say, YOLO, there is a specific value for confidence score, as we have seen for Introduction to Computer Vision. But for those who have not seen it yet, we will cover this very shortly. What we do is we take this one with the highest confidence score, remove it from our list of predictions, right? We remove it from our list of predictions and put it in the final proposal list D. So this list D is an empty list. Initially, it's an empty list, right? And we already know that the highest score bounding box or the highest score proposal is obviously going to be inside our final predictions. Now, what we do is we go through our list of proposals or the remaining list of proposal, which is in B, calculate the intersection over union with this highest score confidence prediction. If the intersection over union is higher than a certain threshold, let's say n, for simplicity, let's call it 0.9, then we can remove that proposal from B because it is a redundant proposal, right? So they are very close to each other. Probably it is the same object being detected twice. So we just remove that one until there is no other proposal very similar to the one that we have taken. Once this is done, we go again, repeat the same task of finding the one that is with the highest confidence score from the remaining proposals, remove it from B, add it to D, and repeat the same process again of calculating the intersection over union, removing anything that has a high overlap, taking the highest confidence point or highest confidence proposal, finding its most related or most closest proposals and removing those which are very similar, repeating again and again and again until we have 0 proposals in B. And basically our list D will be the new list of proposals which don't have any overlaps, or let's hope wouldn't have any overlaps. As you can see, this is an algorithm, meaning it is a heuristic, right? So a heuristic means it's an idea that would typically work in most cases. This is an algorithm that does not work in the cases where people are crowded, right? So let's imagine a situation where you are in a train station and you're trying to detect people. Certainly there's going to be lots and lots of overlap between all the bounding boxes of the different people. And using this non-maximum suppression algorithm, you will be removing the majority of the correctly or deleting the majority of the correctly existing proposals. So non-maximum suppression algorithm is a very good algorithm, but it must be used in controlled settings. So this is something, for example, if you already know where you are going to apply it, you know the distance, the minimum distance between 2 objects in that situation. So you could clearly just calculate or mathematically calculate the threshold n, and from that you could safely use non-maximum suppression. But if you cannot do that, then try to just put a threshold on the proposed confidence score. Just remove any confidence score that is below 0.6, for example, or something like that. So this is something to keep in mind. Non-maximum suppression is a very good algorithm, but it is a heuristic, so it does not work for all cases. Use it with caution. Now, RCNN, this is, as we said, the most basic algorithm, and it is exactly the algorithm we have been discussing so far, right? So it's just sliding a 2D CNN over the image, and instead of doing that directly, we could use the selective search idea to speed up the calculations. So this is what RCNN does. Basically, it will take an image, extract region proposals. This is using the selective search algorithm. Each one of these regions will be sent through the CNN and then basically classified. That's it. Very basic algorithm, nothing fancy, very direct. The selective search algorithm, as we have said, it will generate initial subsegmentations, and we try to generate many candidate regions from this one. And then using a greedy algorithm, we will try to recursively combine similar regions into a larger one, right? So let's imagine first we combine the first or the front of the truck, combine the back of the truck, and using this greedy algorithm, we will combine the back and the front of the truck and propose that as a potential region for an object. And basically, we will use the generated regions to produce the final candidate region proposals. There are many problems with this RCNN. The training time, basically, we will do 2,000 classifications per each image. 2,000 for each image. Let's say we have 1 million images, 1 million times 2,000. That's a very big number that I cannot pronounce. And multiply that, but let's say with 100 epochs. So 100 times 2,000 times a million, the number becomes just too big, and the training will be taking months and months to finish. And that is true. They did train it for months and months, and they actually used it. The inference time is again very, very large. So it's 47 seconds. As you can imagine, it's 2,000 classifications per image. So yeah, even on a very, very fast GPU, 2,000 classifications does take a lot of time, 47 seconds. So it's not something that can be used as a real-time model, but it is a good start, right? Next, the next problem is, again, the selective search algorithm. Selective search algorithm is not dataset specific. It is, again, an algorithm. It is a heuristic. It is not something that is being trained on the data. It is something that is being completely used by default, used in medical images, used in artworks, used in, let's say, sculptures, used in real photos. All of these images cannot be used under the same heuristic, meaning this heuristic will always fail or will always give very bad results for all of these specific types of data sets. So again, heuristic is bad. Try to stay away from using heuristics unless it is in a controlled setting. And this is the problem of the model, mainly summarized in training time, very large, inference time is very large, and the selective search is not dataset specific, meaning it does not give good results. So what we have seen so far is what is object detection, what are the algorithms what are the ways of evaluating and improving the results of object detection, and what is the most basic model for object detection, which we kind of, let's say every single human being can imagine this model. So it's not really a revolutionary model, which is called the RCNN. For now, let's take a break and ask some questions. Do you guys have any questions, especially the people who did not take the introduction to computer vision? So I was going very fast because for those who did not take it, I'm not really sure if it's going to be very important to focus on the details, especially if it's a bit of an old model. But for those who already took the course, so this is quite just a revision for you guys, right? So do you guys have any questions? Nope. Okay, so let's take again another break, say 10 minutes again. Let's come back at 18. And we will finish our lecture on object detection. And then we will just quickly go through the different labs of YOLO v4, YOLO v5, and faster RCNN. For those who already took the course, these are very basic models, and you will see the code is really super easy and super quick to use. So see you soon. Hey guys, I hope you guys are back. So let's finish this lecture. So the first improvement over the RCNN architecture didn't really do much about the selective search problem, but it sped up the calculations of the different passes over the convolutional neural network. Sorry guys, I'll just drink some water. Yep, hopefully this is better. So basically what happens in FastRCNN is instead of selective search proposing different regions, and every time we send it through the CNN, right? So now we send the whole image. Let's draw this one in red. So the whole image is being sent through the CNN. And basically each region in here will have a corresponding location in the, let's draw it in this color, for example. This is the feature map, right? This is the feature map of all of the image. Selective search has proposed this location. So what we do is we already calculated the feature map once. We just find its corresponding location inside the feature map, right? So it's just like a calculation based on the index here. So this is the index of the proposal by the selective search algorithm. And this is the location inside the feature map of that same region, but in the feature map. So this is the extracted information that we use to send for classification. So this one will just grow through a couple of fully connected neural networks for classification, and it will reduce basically the calculations drastically, right? So previously, we would repeat this entire step 2,000 times. Now, we do not repeat it 2,000 times, but we do it only once. And for each one of these 2,000 different region proposals, we only find a mapping inside the feature map. So this feature map is calculated again only once in the start of the algorithm for each image, for the whole image. And every single one of these proposed regions, we will just find its mapped region inside or map location inside this feature map and just send it directly for the fully connected neural network. One very good question that should pop up is, what if the sizes of the different feature maps or the sizes of different regions of interest are different, meaning the sizes, their corresponding feature maps will be different, and we cannot send different size vectors into the same fully connected neural network, right? So because we already know fully connected neural networks require a fixed length vector. We solve this problem by introducing a new layer or a new type of pooling, which is called ROI pooling. So ROI pooling is a new pooling technique, and it's a very simple technique. It will take any shape you can think of. So it will take this one or this one and map them into the same size. So we have seen max pooling before. What it will do is it will take this big image and map it into a smaller image. With ROI pooling, it will take any size and force it to be into the same size that we want, right? How does it do that? Let's take a small example on how does it do that. So this one is good. Ignore the image. I'm just going to try to maybe share a whiteboard. Yeah, I hope you guys now can see the whiteboard instead of the lecture. Can you see the whiteboard?
Yep.
Nice. So let's do this. This is an image, or this is the proposed region inside the feature map. And this is where we want it to be, the reshape that we want to make. So let's imagine this reshape has 3 by 3. whereas this one has 3 by, let's say, 1, 2, 3, 4, 5, and 6. So a person would logically say there are here 3 horizontal splits. So what we do, we make 3 horizontal splits in here. If, for example, here there was 3 and here there were 4, what we would do is the first split, we just give it an extra position. And here we go, we split our original size into 3 different horizontal regions. Now we go for the vertical ones, and we have 3 of them. And another person would do the same thing. So we split them like this, and the last one probably would have a bigger region, so like this one. So what would happen is we would go into this original image. We have region number 1 that corresponds to this pixel. Region number 2 corresponds to this pixel. Region number 3 corresponds to this pixel. What you do, you take the maximum over this region and put it here. Take the maximum of this region, put it here. Take the maximum of this region and put it here. Again, same thing for this one, same thing for this one, and same thing for this one. So as we said, very simple algorithm. What it will do is it will split the original matrix into different regions depending on what is the proposed output size, right? Let's say it's 2 by 2. This one is 5 by 1, 2, 3, 4, 5, 6. So it's 5 by 6, meaning horizontally we're going to have 2 of them. Let's say the first part has 3, the second part has 2, and divide it horizontally, vertically by 2. So this one has 3, this one has 3, this one has 3, this one has 3, right? So here we will combine 9 pixels into 1 value. Here we combine 6 pixels into 1 value, 9 pixels, 1 value, 6 pixels, 1 value. Well, how do we take that value? Using the maximum. And that's it. So it's a very simple algorithm, as we have seen. Let's go back to our lecture. So this is ROI pooling. It's a very simple pooling technique that just takes any shape, regardless of what it looks like, and maps it into the same shape that we expect. And this is just a small visualization of what's really happening. As we said, the feature map is calculated on the first time only once. And our selective search algorithm will give us region of interest proposals, 1, 2, 3, just as many as he wants. What we do is we take the coordinates of the proposed region and we find the direct mapping inside the feature map. In our case, the feature map is 16 times smaller than the original image. So what we simply do, take this number divided by 16, take this number divided by 16, take the width and the height of the object divided by 16, take the width and the height of the object divided by 16. Sorry, this is the width and the height of the object, right? So we take the width and the height of the object divided by 16. There it is. Take the coordinates of the center, divide them by 16, and there you go. So this is how we do exact mapping from the original image to the feature map locations. And it's simply by dividing by just one number. So instead of passing through the CNN again and again and again, we replace this operation of passing through the CNN with a simple and direct division. So division is O of 1, whereas passing through a CNN will take us decades. So this is the major addition that was introduced in the FastRCNN and sped up the calculations drastically. So here we can see, for example, as you see, the training time for RCNN and the training time for FastRCNN has decreased almost 10 times. So it's a lot faster now to train FastRCNN. And the main problem can be seen in this case. So overall, as you can see, the test time or the inference time has decreased drastically. Now, let's see, try to detect the problem. So the blue line in here is what is called the inference time with selective search, and the red line is the inference time without the selective search. As you can see in RCNN, the difference is very small because, as we said, it takes only like 2 seconds. Sorry. let me just, how do you turn off notifications? Yeah, I think I just like close this one. Those games too. And, okay, good. Let's come back. Very well. Yep. So as we said, the blue line is the inference time with selective search. The red line is without selective search. In RCNN, the difference is just 2 seconds. And that's not very big, right? So it's like, let's say 2% of the overall time. So selective search algorithm was not a major problem in RCNN. But now for fast RCNN, this 2 seconds selective search algorithm is now taking majority of the time. And in order to improve over the fast RCNN architecture, the major thing that needs to change is the selective search algorithm, because as we said, it is now taking over, I don't know, like 95% of the time. So this is why selective search must be, we must get rid of selective search first, because it takes too much time for the fast RCNN problem. It did not take a lot of time for RCNN because RCNN itself was a very long procedure, but fast RCNN was very fast and selective search was only slowing it down. And this is where we proposed, or they proposed, a new architecture called faster RCNN. So faster RCNN doesn't make any big changes. So fast RCNN network is still in here, still intact. The same processing is happening with taking the proposed regions and mapping them inside the feature map, and then applying ROI pooling to make them all the same size, and then just sending them for classification. So the fast RCNN architecture is still here. The major change was replacing selective search with a new neural network. So this neural network is the most basic neural network you can think of, right? So it's a simple neural network that we will basically discuss together. So what they did is they proposed this region proposal neural network. And what it simply does is, remember that algorithm that we proposed in the start, where we slide a classifier over the whole image, right? So this is sliding a classifier over the whole image. We said this algorithm is very bad. Why? Because it takes so much time to go from pixel 1 and then go to the next pixel and then to the next pixel and then to the next pixel. Why is that? Because the size of the image is very large and the size of the classifier is very large. So what they said is, what if we could make the image, the search region, smaller and make the classifier also smaller? So what they did, instead of searching for the object in here on the image, they search for the object on the feature map, right? So the feature map is a much smaller matrix than the original image. Here we have 1000 by 600. So moving every single pixel and predicting at every single pixel would be very expensive on the original image. But when we do it on the feature map, it becomes much easier because it's a much smaller matrix and you can parse all of it very quickly. So this is a first improvement. The second problem that we had of basically putting a full CNN at each of one of these steps, it takes a lot of time because one CNN inference is also very lengthy. So let's say it takes 0.2 seconds, and 0.2 seconds is already a lot for just one step. So what they decided to do is replace our big classifier CNN model with only a fully connected neural network classifier. So fully connected neural network means just like 1 or 2 layers for classification, very small model, multiplication and addition. And we apply it on each one of these small regions. So here we are doing the search on these regions. Let's say we are going to apply the neural network 60 by 40 times. 60 by 40 is not a lot compared to 1000 by 600. So it's a much smaller algorithm. And instead of sending it through the CNN again and again, we send it through the CNN only once, right? So this is sending it through the CNN only once. and the search is happening using only fully connected neural network. These fully connected neural networks are called as anchors. So these are what we call as anchors. So each anchor has a different size and shape. So for example, at this point A, we will put different types of anchors. Why do we put different types of anchors? Because objects can come in different sizes and different shapes and different rotations. So instead of just sliding one fully connected neural network through the image, we will just slide different fully connected neural networks with different shapes, right? So one would take this region, one would take this region, one would take this region for rectangular, horizontally laying object or vertically laying object. And as you can see, we have one for very small objects, one for very large objects, and one for very, very, very large objects. Now, again, in this image, it might be a bit confusing as we are showing the anchors on the original image. Remember, the anchors are not on the original image. The anchors are on the feature map. Only thing that we're visualizing here is what are they seeing, right? So when I put an anchor here with this shape, it will be mapped. It will be as if I am searching in the original image with this size. So this is the goal of this visualization, right? Do not confuse and think that the anchors are being used on the original image. They are being used on the feature map. So the RPN, just to summarize again, the RPN is a very simple model. So it's a sliding window classifier. Each one of these windows will have different shapes. Each one of them is called an anchor. Some of them are rectangular, horizontal, vertical, big rectangular, small rectangular, medium rectangular, big horizontal, small horizontal, and medium horizontal. Of course, there are 9 of these anchors, and each one of them will be just a simple multiplication and addition. So it's just a simple intermediate layer, fully connected layer with 56 neurons. So again, we have 256 logistic regressions, very basic calculation, and followed by a classification neural network. Classification neural network will have 2 times k, which is just 9. So it's 2 times 9 scores or 2 times 9 outputs, whether there is an object or there is no object, times the different shapes of the objects that we have here. And of course, we will do some regression classification or regression predictions. These regressions will be the coordinates of the objects. So the coordinates of the objects means here, the X and Y for the center and the width and height of the object. There are many ways to represent an object in an image, but this is one of the most common representations. So here, as we said, there are 4 values for every object. Each one of them is an anchor. So basically it's 4 times 9, 4 times k, or 4 times 9, right? Because k is 9. So to summarize the architecture again, FastRCNN is a very basic model. It's made of FastRCNN architecture. This is FastRCNN, the same thing that we have been seeing from the start of the lecture, plus a RPN. So RPN is here to replace the selective search algorithm. And as we said, the RPN is a very basic idea of searching basically for the objects, but instead of sliding a full convolutional neural network through the image, we inspire from this idea that FastRCNN brought of first mapping an image into feature maps and then searching on the feature maps. Searching on the feature maps, since they are a smaller matrix, will give you faster processing, and basically it will be already a more abstract layer of processing or more abstract matrix that contains much richer information than the original image, meaning you don't have to build a very big classifier to find the objects in the feature map. Only a 2-layer classifier will be very useful for detecting objects in this feature map. So the architecture in a whole is very simple, very basic idea. The FastRCNN, as we have seen, is a very intuitive idea. And the RPN architecture is again a very intuitive idea. So here, one big change that happened recently is instead of using BGG, now we're using pyramid neural networks, and we will speak about these pyramid neural networks soon in the lab. So a quick recap of the RCNN family. We started with RCNN, which was using selective search plus sending every single one of these proposed regions through a convolutional neural network, which took a lot of time. We found that it's a lot of time for us. So what we did is we kept selective search, and instead of sending each one of the proposed regions through the CNN, we send the image once through the CNN, and each one of these regions, we find their corresponding location on the feature map and send it for ROI pooling and classification. And then we saw that the selective search algorithm was just sadly taking too long for us to work with. So we replaced it with RPN. So RPN is just selective, it's just a it's just a search model or a search neural network that is searching on the feature map to increase the speed of the search, and basically searching on a abstract and rich matrix instead of the original image, and using only very basic 2-layer classifiers, and it's using different anchors to accommodate for the different shapes and different rotations of the objects. Once the RPN has concluded, again, RPN is very fast. Why? Because the search is very parallelizable, right? So when you look at it like this, it's a sliding window. This is how we are describing it, but it can be thought of as just not a sliding window, but each one of these is being done at the same time. So this would leverage the architectures of GPUs. We have multiple calculations at the same time. We can go through the full feature map, send each one of them, all of these anchors at the same time, calculate all of these multiplications and additions at the same time. And the whole RPN calculations can be done very quickly on a GPU, right? So this is very useful for GPUs, and the RPN, although it sounds like a search algorithm and a sequential technique, but it is something that is easily parallelizable and gives very good results since it is easily parallelizable, right? So on GPUs, it is very, very fast. So we come back here again. So we have RPN combined with the old architecture of fast RCNN, and this gives us the faster RCNN. Now, on the next few lectures, we will speak about mask RCNN, which is an architecture for instance segmentation. Keep it in mind, it's very similar to our fast RCNN architecture. And yeah, basically it will only add a small mask predictor. We will see what these changes are pretty soon. So let's take a small break here and ask for questions. Do you guys have any questions so far about the content that we have covered?
No.
No questions?
Yeah, most of us just covered it 2 months ago.
Yeah, exactly. So I'm sure you guys already remember all of this, but for example, I think Lev and Ozzy, for example, this is something new, and maybe Dimitri or someone else, maybe this is completely new for them. So do you guys find this a bit challenging? Is it too complicated? Is it not very logical?
It's all right, but I would rather come back to it in a recording.
Yeah, certainly watching it again. And once we go through the lab, you will see all of these different architectures in motion. But the most important thing is the faster RCNN. Fast RCNN and RCNN are only here for reference, such that to simplify basically the understanding of the faster RCNN architecture. Now let's move on a little bit more. One of the most common words that you will find in object detection is the word Detectron. So Detectron is a library created by Facebook, and the goal of it is to implement many computer vision models and to simplify their coding. So basically, instead of you having to program all of these architectures and their training steps, because the training steps of these models are just humongous. So what they did is they already written the model, the training algorithms, fine-tuning algorithms, and all of that for you. So only thing you have to do is just a few function calls and a couple of configurations, and you have the model directly. It is written fully in PyTorch, so you can access the model, you can access every single layer, you can access every single activation of every single layer. You can do everything you want to do. Since it is written in PyTorch, you have full access and full control of what happens. It provides a list of pre-trained models for all of these tasks, such as object detection, object segmentation, dense pose, estimation, panoptic segmentation. Panoptic segmentation is this one, right? So basically every single pixel in the image must have at least must have a class, right? And landmark detection is what we are seeing here. So we are estimating different landmarks inside the image. Now the next architecture that we will speak about, and this is a new family of models called the YOLO model, or you only look once model. This one is exactly what you would assume RCNN would have been, right? So if you have, if somebody described to you RCNN without showing you the architecture, you would probably think of YOLO first, right? So what it does is simply, you take an image, slide it through, send it through a couple of CNNs, and you would get a feature map. Remember, previously what we were doing is on the RPN, right? RPN is already doing the object classification, which is class, object or not object, and it was doing the, what is it called? Help me out. Landmark, not the landmark. Forgot the name. Bounding box regression, right? So the RPN is already doing the classification and the bounding box regression. So why should we just use this RPN only to propose regions and not add on top of it another just classifier that does the object classification, right? So here we say, is it an object or not? So this is the object classification or the objectness classification. And here we just have our classes such as dog, dog or cat or whatever we want, right? So this is what YOLO is. This is what YOLO is doing. Basically, it will send it through a couple of CNNs. We get our beautiful feature map. And on this feature map, we will do the following. So on this feature map, we will do the following. We will put different boxes. Let's ignore why do we have different boxes for now, but at every single one of these pixels, we will predict the following. We will predict the bounding box coordinates just the same way as we are doing in RPN. We will predict the objectness score the same way we are doing in RPN, but instead of just that, we will add the prediction of the class scores. So basically, is it a dog? Is it a cat? Is it a horse? Is it this? Is it this? Is it that? As you can see, we are repeating this task multiple times. Why? Because we are going to apply different types of bounding boxes. So like this, and like this, right? So we have 3 types of bounding boxes, and this gives us 3 types of classifications, right? So we will just repeat this value 3 times. We repeat this process for 3 types of objects. So here, as you can see, we have the ability to predict 3 types of objects, but RPN is able to do the processing over 9 types of objects. So how can we solve this problem for YOLO? Simply, we repeat this at multiple scales. So what they are doing, right? The first scale is for the largest of objects. So let's say in the original image, there was an object that is very large. If we just send it through a couple of convolutions and reduce the size of the feature map a lot, we will still be able to find information about that large object in this smaller image. And basically, we can do the object detection for the large objects in this scale. What they are later doing, simple, they just upscale from this place forward, combine it with the previous convolutional feature maps, and basically they would get a much bigger image, right? So usually previously what we expect from the convolutional neural network is that the feature maps as we go deeper and deeper inside the neural network, the feature maps will get smaller and smaller. But in this case, the first scale has the smallest feature map. And then we apply this upsampling. So upsampling will increase the size of the feature maps, and the next layers will be much bigger. Again, we repeat the upsampling step, and the next feature maps will be even bigger. So for the medium-sized objects, once we just shrink the size, for example, 16 times, we still can find information about the medium-sized objects. So here we apply 3 boxes, and we get our beautiful medium object detection. Here we had our large object detector. Here we have our medium object detector. Now for the smallest object detector is we will require to basically upsample even further. And here we don't scale the image down too much. We have just a 8 stride, meaning even the smallest of objects should be still visible or locatable inside this feature map. We repeat this for 3 types of bounding boxes, and there you go. You have for YOLO the ability to find 9 types of objects. So 3 for large objects, 3 for medium objects, and 3 for small objects, just as you would in RPN or RCNN. Now, one very, very good question would be, why are we doing it in the inverse, right? So probably if we just do the detection of the smallest objects in this step directly, because we have a big feature map, that would save us a lot of calculations, right? And of course, doing this, for example, for the medium, we could just do it directly on this location because the size of the feature map is more appropriate. Why do we make this feature map smaller and then make them bigger and then make them bigger again, right? Just use an already big feature map. This is a very good question, and the answer to this one is the following. Starting to work with the large objects will give you a rich understanding of the image. So basically, this feature map will give you a much better understanding of the global idea of the image. Whereas this one is still not able to understand the global location of the objects. So this small feature map is very condensed and contains very good information about the location of the bigger objects. Now from here, we upsample, combine it with the previous feature maps, and like this you get both the size that you want, the same information that you would have in here, but you add on top of it with just a simple concatenation, you add on top of it the information that was used to detect the large objects. So first you have local information in the medium region, plus you have the global information of what is happening for the larger objects. And then again, for even the smallest of objects, you have both of these information. You have the information for the largest of objects, and then the medium of objects, and again, the details needed to find the smallest of objects. So this one is, this is the idea that they used to improve basically the results. Instead of working on the small objects and then the medium objects and then the large objects in the end, we work first on the large objects, then on the medium objects, and then on the smallest of objects because they're the most difficult to find. This is YOLO, this is Detectron, this is RCNN, this is fast RCNN, and this is faster RCNN. We have seen all the architectures, we have seen the intuitions behind, we have seen why are these models working the way they are. Now, do you guys have any questions about these models? If not, then we can go for the labs and see how do we train each one of these different models. Any questions? Especially from the people who did not take this before. Nope. Let's then take a small break, a 10 minutes break, and come back to do the labs. And after that, mic is not working, but overall idea is clear. Thank you so much. You can repeat, go through them again, and that would give you a much better understanding. But we will go through the architectures in the labs, and you will have a much better understanding of all of these information. What did I want to say? I forgot. Yeah, let's just take a quick break and come back. We're not going to use any basic previous material. I'm going to start from scratch and show you guys how you would train very quickly any object detector that you want, right? So I'm just going to start from scratch, not going to use any of the code that I have, going to use only code that you can find easily on the internet. And very quickly, we can get it running in less than 5 minutes. You can have any model you want. So see you guys after 10 minutes. So let's say 05. Just so I understand how much time is left and how much time is not left, because there with this like new change of times between Russia and France, I have no idea. So what time is it in Moscow? In Orpus?
Almost 8 p.m.
It's almost 8. Okay, so almost 8, and we finish at what time the course? 21 at 9:20, right?
Yeah.
Okay, nice. So let's come back at 8:05. See you guys soon. Hey guys, I hope you guys are back. So let's start with the first model, which is the RCNN family, and mainly the faster RCNN or the mask RCNN architectures. So as we said, Detectron is a library created by Facebook that implements all of these architectures and allows you to use them in a very simple manner. If you come to their README in here on GitHub, you'll find lots of information about the project. Not a lot of information on the code, but a lot of information on how to use the model, right? So here you'll find some installation guidelines if you would like to install it on different architectures. And the most important part for us is either you see this getting started guide. This will give you some information, but the better one is to use the Colab notebook to learn how to train basically faster RCNN architecture on different data sets and how can you read the data. So this is the Detectron 2 beginners tutorial on faster RCNN. You'll find lots of different models in here, but we will not really focus on those. So let's just go down a little bit and see what are, for example, presented here. So this is for panoptic segmentation, as we have said. And you will find some other things such as panoptic segmentation on video. So you'll find the code for this one is pretty short, as you see, but we will not use this one. So first, let's copy this one to our drive. And as I said, in less than 5 minutes, we will have this running on our datasets. Here we go. So first, let me just delete the extra parts. Other types of built-in models. Again, this is extra parts. Now let's just come here, make sure that we are using the correct runtime, GPU. Good, run all. So the first part of this code will be just installing basically the different dependencies that we need. Mainly it's different versions of CUDA and different versions of Torch. We're not going to install CUDA, but we're just going to make sure that it is a correct version. And after that, this is just some obligatory basic imports from Detectron. This is just for cv2.imshow. If you already worked with cv2.imshow, it does not work on Colab, so they have their own version, which is just a different one, but to simplify the function calls, and just some basic imports, mainly OS, because we are going to read some files from the we're going to read some files from the hard drive, and JSON, CV2, and random. Next, we're going to download a random picture from the internet. Here it is. So this one contains just lots of different objects, and this is the goal of this visualization, just to make sure that, or to see if the models are actually doing a good job. So here you can clearly see what we are doing is we are creating a config file or a config variable. You can do this like manually using config files. So basically there is a config file and you would just go through this config file. There are different levels. So for example, there is the model level, there is the ROI head inside the model level, and there is a score threshold test variable inside this level. And you just set its value to 0.5. Preferably don't work with these values directly, but work mainly on the variables here. So instead of going through the files manually, preferably just use this already existent architecture. So just to make sure we have our beautiful Detectron already installed. It's not already installed. Restart our runtime. Yep. Now everything should be working well. You restarted the runtime? No. Get config is not. Okay, run this. Run this. Yeah, nice. So now hopefully everything is working very well. Why did I do this restart runtime? It's mainly because there are some packages. So the following packages were previously imported at this runtime, and we're using a newly installed version of them. Mainly it's called PyDavid plugins. So because of this, because of this package had already an older version inside Colab, whereas Detectron requires a newer version. So we had to restart the runtime and preload the new package instance, right? The newer package Well, let's just say the newer package version, right? We rerun the imports again. Simply just show this image. Now as we said, we're creating a new config. This config is just basically a description of the model. So the first level is basically what is the pre-trained architecture you're going to use, and what are the pre-trained weights that you are going to use. So this is very useful because you're not going to train something directly from scratch. So always remember to use pre-trained weights and pre-trained architectures or pre-existing architectures. I think we could take a look at this YAML file. Let's just go for it. So there you go. Simply, it has a simple config, and mainly it contains the following. So the model weights are the following. So this is the location of the model weights by default. Mask on is true because we have our beautiful Mascar CNN, I think, right? This is Mascar CNN. Some more information is using ResNets, depth 50. This is just for information about the solver. Solver is basically what you would say a gradient descent training algorithm, or the trainer in general. So solver is just a term used for majority of models in general. So basically you would get things like training iterations, prediction function. All of these functions are inside a solver class or a solver, what is it called? A solver file. This is just a beautiful way of segmenting your code. And here, for example, these are the steps that will be used to save different versions of the model. So this step means 20 or 210,000 iteration. We will save a version of the model. At the 250,000 step or iteration, we will save another version of the model. And maximum iterations means the maximum number of iterations we pass through the data sets. And basically how many batches we will load from the data, and that is 2,700,000. If you can see, the base config file is called base RCNN FBN. And if we go through it, let's see. Oh, it's not here. Configs base RCNN FBN. Here it is. So here you'll find a bit more information. So you can find the output features for ResNet, the backbone name, the FBN, which is feature pyramid networks, the anchor generators. Sorry. These are the different aspect ratios for the different what are they called, anchors. More information about the RPN. These are the information for the ROI heads, ROI head box heads, sorry, ROI mask head, the data set locations, such as the name of the data sets and the name of the testing data sets. These names will be mapped in another class, namely called, not in here, let's go down a little bit more, but there it is, yep. And this is called dataset catalog. So basically the name in here must exist in the dataset catalog of PyTorch, so not PyTorch, of Detectron. So we will register our datasets inside this dataset catalog. And just by putting the name of the dataset in this config file, you will be able to run the training on it directly. And again, this is just for the solver. This is images per batch, base learning rate, maths iterations, we spoke about them, and steps, we already spoke about them. Useless stuff. So here you'll find different other architectures that you can look through. And this is very important because in your homework, I will ask you to find another architecture in here. Mainly, let me find it for you guys. faster. This is fast RCNN. I'm not going to ask you for fast RCNN, but I'm going to ask you for faster RCNN. And I would like you to use one of these faster RCNN models to train a model. But for now, in our case, we're going to use the mask RCNN architectures. You will see that there's no main difference between them in the code. Only thing you have to do is basically change the base config file and the base checkpoint where you will find the, well, from the model zoo where you will find the pre-trained weights. Once you have this config already done, as we have seen, you can do either configurations using files directly from here or manually change them, or you can just get the file and manually change it like this, right? So config, remember we saw a level called model. We saw inside that model level called ROI heads, and we saw inside that we could make a, what is it called? A variable where we put the score threshold test. So this one, anything that has a probability of being an object less than 0.5, we do not show it to the user. And yeah, we create our default predictor directly like this. So default predictor using the configs, and you can use it just out of the box, right? So you give it the image and you get the predictions. It just as easy as that. This is the image, you read it from CV2, you give it to the predictor, and you get the predictions. Very easy, very basic, very direct. Let's try to do the following. Let's check what is this predictor. Are there any information inside the predictor, such as the model? Here you go. This is the model that we are using inside, what is it called? For our default predictor, you see it's using FPN, which is feature pyramid networks. We will speak about feature pyramid networks once I just go through all of these details, but basically it's just a couple of convolutional neural networks, as you guys can see here, right? Here you should find more information about things such as ROI heads. You should find ROI pooling somewhere also. ROI pooler. Yeah, basically just the things that we have seen before. So this is the mask RCNN part, which we have not seen. So this is something a bit extra, but for the rest of them, we already have seen them. So this is for classification, I think, right? So this is number of classes, which is 81. And this is for the bounding box predictors, which is, I think, 81 times 4, right? Can somebody confirm if this is 81 times 4? It doesn't look like it's 81 times 4. I'm not sure why is it 320. Maybe it's something else. Let me see. 320 divided by 4. It's 80. Okay, so probably there is one class that we don't have its bounding boxes, or we don't need their bounding boxes, or maybe we have an extra class in here for background, something like that. Now let's analyze the output, right? So as I said previously, right? So this is written in PyTorch. So if you would like to access any of these layers, access the weights of these layers, access the activations made by these layers, access, for example, for those who you have seen, like we did a lab on model interpretation using GradCam, and we saw what are the different steps of GradCam. And during the different steps of GradCam, we needed to calculate the gradients, right? The gradients of the predictions with regards to the feature maps. So now you have the full access to the model. You have full access to every single layer inside this model. You can have full access to the gradients that are being calculated, and you can apply GradCam for object detection very easily. Now let's go back to the outputs. What is inside this outputs object? And if you look at it, it's basically a dictionary that contains just one. So let's just, I'm not sure if it's just one, but let's see .keys. But there's just one important information, which is instances. Yeah, it's just one, right? It's a notebook with just one main value, which is instances. Let's just delete this one. Let's see what is inside this one. Again, instances in an object. It contains the number of instances, meaning the number of objects found in the image, 15 in this case, contains information about the image. And this is now the most important part, which are the fields. Fields are predicted bounding boxes. Here they are. for each one of these objects. Now, scores for each one of these objects. So you'll see that each one has different scores. There you go. So this is the scores of objectness score, let's call them. Predicted class. So you will see that this 17, 0, 0, 0, 25, 0, 0, 0. Yeah, there you go. And now the predicted mask. This is not something that we will cover during this lecture, but basically it will give you the mask of what pixels belong to that pixel, belong to that object. So if we go here, majority of them are false because these are like the boundaries. So nothing really is important happening in the boundaries here. But basically it will tell you this pixel does not belong to the object. This pixel belongs, so this pixel is true. And this is what you get in this, where is it? Yeah, this predicted masks. So you have two things, which are predicted classes or predicted boxes. And this is how you can access them directly. For visualization purposes, again, Detectron also comes with a visualizer that would simplify all this process for you. Instead of drawing the bounding boxes, writing this one, writing the score, all that will be done by Detectron for you by default. You just create the, what is it called? You just create the visualizer. In here, we don't have really a data set, so we're using the original data sets of, we're using the original data set used for training, which is probably Coco something, right? Let's go for faster RC Ninja just randomly, and not here. Let's go to the base one. There it is. Data set, yes, it's Coco 2017 train. So this is the base meta catalog that we're that we are using for the visualization. If we have something that is something that we made, then we just replace this one with the value that we have. And there you go for the visualization. Now let's go and try to prepare to work on a certain data set. So this is our new data sets. This is called the balloon data set. It has train and validation values. The validation images contain images, of course, here they are. And of course, a beautiful, no, not a beautiful, and a beautiful JSON that contains all the information about the objects in the in this image and in the images of the validation. So we come here, for example, name of the image, and then it's so big that the process is being very slow. So here, so this is just file reference, useless, size, file name again, useless, file attributes, regions. Now we are speaking, right? So this is the regions of interest. So this is the region of the object, and this is represented using a polygon. What is a polygon? So a polygon is just a shape like this. That basically surrounds your object. So it's just a set of points that would surround your objects. And here you have the X points for these points that surround the objects. And probably here you have the all points Y again. For people who don't know this one, it might be useful to check out, for example, something. Oh, well. What happened? This is bad. Login. Yeah, I think their website is a bit crashing for some reason. I don't know why. Login. So this is a cool website for building different, for example, what are they called? Annotations to annotate data. And you will see what polygons are in here. So this is a polygon for an object called harp. So if you see, we are depicting the location of the harp using different points surrounding its contour. And these are what polygons are. So basically the polygons that you are looking for, that list contains the coordinates of all of these points that make up your, what is it called? Your objects. So this is what you'll find in this JSON file. Of course, our beautiful Detectron can work directly with these JSON files, so you can read them like this. But we would take the longer road, which is reading it manually. So what we will do, we will read the JSON file, and then for each JSON file, we will just load it and create basically this dataset dictionary. Dataset dictionary, I will go quickly through this code because this is just basic Python code. Dataset dictionary contains a list of records. each record contains the following information: file name, image ID, height, width, and different objects that are inside this this image. So the different objects that are inside this image are called annotations. And of course, it is a list that contains the following information. Each object contains a bounding box, contains the mode of this bounding box. Again, we said there are different ways of representing bounding boxes. There could be the following, right? So either the top right corner and the bottom, no, top left corner, bottom right corner. This can give you how the bounding box is looking like. Another one would be the center plus the height and width of the object. So in here, you could specify the different box modes. And this is for segmentation. You would specify the polygon for the segmentation. For the case of object detection, there is no segmentation, so you do not use this one. And category ID in this case, and only in this case because we're working on balloons, we have just one class and it's always class number 0. But if you have like other classes, you would put the class ID in here. And the class ID should map to the index of the class you want inside this thing classes that you set in the metadata catalog. So the metadata catalog, as we said, as we saw in here, we must register these two data sets, and we register them in the following manner. So dataset catalog, register balloon, train, balloon validation, and we just make a function call to load all this dataset dictionaries from the JSON file for the training data and for the validation data. And then we also register it in the metadata catalog, and to set basically this classes, the list of classes of this dataset. If you have just one object or one class, you put here. If you have multiple, then you put class 2, class 3, class 4, class 5, right? Very well. Now, just to make sure that you have read the dataset correctly, usually this code will just sample randomly 3 images and show you. If everything is done correct, you should see something like this. Now for the training is going to be very similar to what we have seen in the inference before. Basically, we create a config, right? So we go back up. We create a config from pre-trained instances and just specify what is the learning rate, specify all this information, and we'll launch the training directly. So again, we said we create config, create what is the base configuration file that we use, what is the base weights that we use, number of workers to use for the data loader. This is also useful. What is the training data name that was already registered, right? So this is the name that we registered before. What is the test data name that was already registered? If you have something, you put it. If you don't, you just leave it empty. Images per batch, this is just something for how many images will you load for, will you train on at the same time, which is basically your batch size, right? The base learning rate, this is the starting learning rate for the training. How many iterations will you load? So how many iterations will you go through the images? How many times will you, how many steps will you take for gradient descent? This is steps. Usually you put 80% of, sorry. Yep. 80% of your max iterations. So in this case, let's say it's 250 and then 275, just like a potential one. You could just save different ones or save nothing completely, right? Batch size per image. This is basically the how many. Remember when we said through the ARP, through the, what is it called? Region proposal network, we're going to slide different anchors. How many of these anchors will you be sliding at the same time, right? So 128, this is for parallelization and will speed up basically the operation of search. And the most important one is how many classes do you have? And in our case, we only have one class. If you have multiple, you could set multiple ones. You could check this repo for more information about different configs, but we have seen the different config files and we went through them already. So this is just something pretty optional. This one is just to make sure that we have a place to put our output, basically the output of the training. The output of the training is the following. We have the matrix.json, and this is basically your training history. you will have the loss functions, you will have the accuracies, you will have the different things that you need. And basically here you will find things such as the trained model and other things, right? Let's continue. It starts by showing you, just the next code, default trainer, resume or reload. Resume equals false because we're going to start from scratch. We're not going to continue training from previous iterations. We just started, and meaning we will use basically the base learning rate to start with it. If it was resume equals false, there will be some calculations to find the perfect learning rate and stuff like that. If not, we can start the training directly. So for example, trainer.train and continue. So here, for example, we have the architecture. As we said, we will not speak about feature pyramid networks right now. We will speak about it once we finish this lab, because it's a very simple idea again. And this is the architecture. It will show us different information also about how many instances and how many classes do you have. If you have multiple classes, you will see how many training classes per category. Here you will find how many removed images with no usable annotations. None of them were removed because sometimes you can find an image in your dataset with 0 annotations, so they're just not used for the training. So here we can see, for example, I stopped. Let's see. It's not registered. So let's run the code, right? We already downloaded it. Register this one. Run this. Nice. Let's start the training. Let's hope it wouldn't take a lot of time. Usually it wouldn't take a lot of time because it's a small data set. So let's see. Yeah, 5 minutes left. For now, let's start explaining, for example, these parts. So it did load all the values or the pre-trained weights, but there are some weights that were not used. Mainly the classification score weight, the classification score bias. So basically, we're not having the same classes. So the final layer for classification will not be the same. Previously, we had 81 classes. Now we have 2 classes, basically our class and the background. And here we have 81 class. Again, same thing for the bias, not compatible shapes. Same thing for the weights of the bounding boxes. Sorry. And of course, for the mask head. So this is just how many classes do we have for the prediction of the mask. And while we are doing the training, you will find the following information. How much time is left for the training? How many iterations have you already covered? And things such as the total loss, classification loss, bounding box regression loss, mask loss, RPN classification loss. So this is the region proposal network loss, lesion proposal lost. So this one is just basically to make sure that the bounding box regression is done in a clean manner. No need to really go too much into it. This is how much time it is taking, date time. So this is just how much time it's taking again to run this beautiful algorithm. Learning rate that we're using, it's very close to the learning rate that we set, and then it's going to be changing depending on the algorithm or the scheduler of the trainer. And here we have the maximum memory that was used during this training. So it's like 2 gigabytes, right? 2 to 3 gigabytes. While we are waiting here, so there's nothing more for us to see in Mask RCNN or Faster RCNN. The rest is exactly the same. So let's just leave it training and go to the second part of the lab. First, do we have any questions about Mask RCNNs or Faster RCNN architectures in Detectron? We have seen how to read the data. We have seen how to select the pre-trained model, and the rest will be exactly the same. You will play a lot with this during your lab, your homework, because I'm going to ask you to basically run all of these models and give me the results. So you will have more experience with that soon. Now let's run to the different versions of YOLO, and instead of going through YOLO directly, we're going to speak about RoboFlow. So RoboFlow is a very, very useful website that if you are working in computer vision, you should be always using. First thing, it provides you with lots of cool data sets, computer vision data sets that are provided to you for free, and you can easily download them in many of the popular formats such as JSON, Cocoa JSON, Pascal, VOC, XML, YOLO version 3 versions, and TensorFlow TF records. For your convenience, we have also downsized and augmented versions available. Let's take the simplest one, smallest data set. 6-sided dice data set. Okay, now 500 images. This looks good. Thermal dog and people dataset. It has 200. This is even better, 129. Mask dataset. Okay, we have COVID, so we could use this mask dataset. Yeah, let's go with the mask dataset because we have COVID. Yeah. There you go. So this is just a dataset with people wearing masks or not wearing masks. So we come here, download. It tells you what is the version that you want. I wouldn't really go to the version itself, but I would read the name of the versions. Here we have YOLO Darknet. This is a very important version, and YOLO v5 PyTorch. So as we said, there are two main versions for YOLO, which are YOLO v4 and YOLO v5. So let's not go for YOLO v4. Let's just go for YOLO v5 first. YOLO v4 first. YOLO v4, the main source for YOLO v4 is this Alexei AB. He's the guy who did it. He's a Russian researcher in Moscow, and he created the YOLO v4 architecture. People are saying it's the only version of YOLO that is actually peer-reviewed, and it's the only research version of YOLO v4. And other people are saying YOLO v5 is actually very useful, and it is provided to us by this Ultralytics company, and it's not an article, it's not a paper, it's just a code that is out there. Personally, I've used both, and I kind of like YOLO v5 too, right? So YOLO v4 is very good, but YOLO v5 is also very good, right? So you could use both. So the main repositories are Darknet and PyTorch based. So Darknet is a very simple, not simple, but a very complicated, I would say, framework for building neural networks, and it's a very fast one, right? So it's completely based on C++. It's what you would say, this is TensorFlow for C++, or this is PyTorch for C++, right? So it's a framework to build neural network for C++. It's very fast. And the authors of YOLO v4 decided to implement this architecture in Darknet, whereas the authors of YOLO v5 decided to implement it in PyTorch. So you just come here. I would like to work on it for YOLO v4 on Darknet, for example. You continue. And easily what you will find here is this beautiful code. You copy it, choose your model. So there is YOLO X. This is an architecture of YOLO. There is YOLO v5. You can get its notebook in here. There is YOLO in R. YOLO, you only look once representation is a state-of-the-art object detection model that pre-trains an implicit knowledge network and a set of parameters that represents explicit knowledge. There is scaled YOLO v4, which is a very beautiful architecture that I really like. And I think this one is implemented in PyTorch. There is efficient detection or efficient det. It's also a very beautiful one. This is YOLO v4 Tiny, the best model that you can use if you are training on Colab. And you have the beautiful YOLO v4 Darknet. If you're working, for example, on Detectron 2, again, you can find its notebook in here. As I said, you can find all the beautiful architectures of all the beautiful models that you know in this list. And how do you get started on it? As I said, it only takes 5 minutes to run on any algorithm you want. 5 minutes, you just select the data set, select the data downloader you want, and you come here and choose the model you would like. You chose, for example, YOLO v4 Darknet. Go to its Colab notebook, free GPU. And there you go. You have the code that runs for all the different architectures. We will go through the code again, but the main thing that you need to basically change is the following, or the only thing that you need to change in this architecture is the following. Sorry, here it is. Not this one. Yeah, here it is. So as you remember, I showed you in here, for example, let's come back again, YOLO v4, where is it? YOLO darknet txt, there it is. So YOLO darknet txt, show download code. Yep, there it is. You just copy this beautiful link and replace it in here. That's it, and it will download the data. The rest of the code will work perfectly for any type of data set that is downloaded from RoboFlow. So this is why I said it's like very simple, just 5 minutes task. You just choose what you want and just download the data. Let's choose another model at the same time. YOLO v5, for example. We're not going to go into the details of them while during the lab. We will go about them after we finish the lab. We will see what is YOLO v4 and what is YOLO v5 and what are the differences they made. But basically, it's just YOLO v3 with a bit of salt on top of it. So again, as we said, so here, replace this code with the code that you got from RoboFlow, and you have the downloader running, and all the rest of this will be working perfectly. I hope now our code has finished. Yes. Now let's go back to Mask RCNN for the final results. So you can see the total loss has decreased from 1.9 to 0.33. This means there was a lot of learning happening. Classification loss decreased from 0.5 to 0.7. So this is amazing. You can come here, see this beautiful tensor board, and see how things have been changing. So for example, I think they show you things such as, yeah, fast RCNN results. This is the bounding box regression loss, classification loss, how it's progressing, mask loss, how it is progressing, the learning rate, how it is changing. So you can see that the learning rate has been changing in a certain pattern. Yeah, these are just different losses, different information that you could check. Now let's run inference using this model. So this is the output, as you can see in here. For example, you have the metrics.json, and this tells you the history of the changing of the losses and the metrics that you chose. Here you will find different things such as the final model, different versions of the model. I think this one contains information about the data set. Yeah. So basically, in this output, you will find lots of information about your data. And now we are running some inference, and you can see the model is actually doing very good. You see, Mask RCNN, it's very fast. It trains very fast. In 5 minutes, you already trained a very, very accurate, you can see, instance segmenter in less than 5 minutes. Trains very well with very few samples, right? Now, how do we analyze if it is good or not? We do that using mainly mean average precision or average precision. So here you come, you find average precision. This is 80%, amazing. 75%, amazing, right? These are results that are very, very good. Anything that is above 60% is already amazing, right? This is the threshold that you would say 60% and onward is a very good model. So 75% means it's a very, very good model. How do we interpret this one? You can, for now, think about average precision as just prediction, or as classification, what is it called? As accuracy, right, for classification. But we will speak about how it is calculated right after we finish the labs of YOLO v4 and YOLO v5. So let's come, for example, I think we finished from this one. Let's just release our beautiful resources. Connect, manage resources, manage sessions, terminate. Nice. Yep, runtime disconnected. YOLO v5, YOLO v4. So YOLO v4 is a bit of a hustle, mainly because it's written in C++. So installation is not going to be as simple as just pip install. It's going to take a lot, some steps. So first, we just confirm no need to confirm it because we know that that Colab comes with the latest versions of CUDA and cuDNN and are already installed for you, and you have NVIDIA installed here. All of the drivers are good. Very good information for those who are going for industrial projects and will install darknet, for example, on different architectures. You will need information about the architecture of the GPU if you're using a GPU. If you're not using a GPU, then this step is completely useless for you. So if you're using a GPU, you need the following information. So basically, this is just some architecture information about the GPU you're using, mainly this architecture and code version. And either you can Google, either you find them here directly, because these are the latest versions of the GPUs that are commonly used. If you cannot find them here, then just Google your GPU name followed by the ARCH and code, and you should find it in the first link, right? Let me just run it, right? Anyway. Next step is to basically clone the darknet repo. So this is the repo from RoboFlow AI. They changed some content from it just to make sure that it's easier to run directly in here. And what we will change is the following makefile. So the makefile is the place where you just change what you should install and what you should not install. So for example, if you do not have a GPU, you set this value to 0. If you do not have QDNN installed, then you set this value to 0. If you do not have an OpenCV, not PyTorch or Python OpenCV version, but the C version of OpenCV installed, if you don't have this one, you can just set it to 0. If you have it, it's going to speed up a lot the calculations. And I think this is the important parts, right? Yeah, just the GPU, QDNN, and OpenCV. Once you did that, also you could change the ARCH value from this, from what you have gathered in here. And the rest is basic, right? Now we're installing our beautiful architecture. So we're installing darknet. And this one is just the same version of installing any C++ code. So basically you change the makefile and then you call make. So changing the makefile, as we said, you just change OpenCV, GPU, or QDNN. Whether you have them or not, 1 and 0 means yes or no. And you will get lots of this very weirdly looking code. And you might think that this is bad, but this is good, right? This means that things are good. If you start seeing lots of red things and lots of errors, it means it's not good. Yeah, now you're just going to download some pre-trained weights, and we will speak about that later on. Now for the data, as you can see, the data set has stopped. We come here, YOLO darknet txt, show download code, and I will copy this one and bring it here. So here it is downloading the data. Data is downloaded. So yeah, let's just repeat. We are inside here. So yes, valid, train, and test. So these are the images and their configs. I think that this one needs the data to be in a certain location. So they changed a little bit the code to make sure that you can use your API, but since I don't really want to share public APIs and stuff, so we're just going to ignore this one, and I will manually change the dataset location. So the dataset location is just tac, 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 and tac. And tac. Nice. Do we have anything else that is referencing their API? Nothing. Direct. Let's hope everything works. So yes, dataset location again. Let's just put it here, remove this beautiful one, remove this beautiful value. And maybe if I run it directly, nothing bad will happen. Yeah, it already exists. I expect this one will be a bad problem. But I think other than that, nothing bad happened, right? So the results are working well. Again, we're the dataset location thing. There you go. Nice. I hope they don't have it anywhere around here too. Yep, nothing bad seems to be here. Yep, run. Everything's good. we will speak about this later. Let me just run the trainer and make sure everything is running. Yep, it is reading the model. Let me see, should have started yet. GPU. Now it should start. We allocated CUDA. Start training. Just to make sure that it started training, so that we don't waste a lot of time later waiting for it. And yeah, I think this one is which model? It's the big version, so it's gonna take a lot of time. Yeah, so it did start. There we go. So this is how much time is left. An enormous amount of time because it's a big model. So I'm just gonna leave it train for now because I don't really care about it a lot, but I will first come back and explain the code, right? So as you have seen, we just extracted our data. We fixed up this code a little bit. What this code is doing is just setting up the locations of the data. So in order to understand it perfectly, we should come to this beautiful README, and it's a very detailed README. So here we see pre-trained model, training from scratch. Can you see training from scratch? Requirements, how to train to detect custom objects, right? How to train to detect custom objects. First, you completely ignore because nobody's going to train YOLO v2 or something like that. But if you want to train YOLO v4 or YOLO v3, what you will do is the following. First, you specify what is the config file you want. What does this mean, the config file you want? Let me just open the same repo in another location and we will understand it better. So basically, we have the following. There are different versions of YOLO v4. If we come to config in here and just type YOLO v4, so here we will find all the different versions of YOLO v4, mainly YOLO v4 MISH, SWISH, CSP, different versions of SMISH and SWISH with CSP, different version of MISH and SMISH with not CSP, yeah, with 4X, different versions. So this is the most default version of YOLO v4. This is what we probably have seen in the course. And what you find here is just the configs, batch size, subdivisions, height and width, number of channels, momentum, decay, angle. All of these just are values that you already know, right? Learning rate, max batches, policy, steps, useless stuff. Now you come to the configuration of the data. So here you'll find this is the downsample road with convolutions, and the activation equals MISH. So a very good indication already that MISH word that you find or SWISH word that you are finding in different config files is just a different activation function, very similar to, what is it called? To ReLU, right? So MISH is an activation function that looks like this. I don't want you guys to focus a lot on the formula of it because the formula is pretty stupid and basically I think, as I remember, they just found it randomly by doing a reinforcement learning random search. So yeah, so this is just another version that is looking very similar to leaky ReLU, but it does not go to -infinite. So it just comes back to 0 if the large becomes infinitely small or infinitely negative. They're saying it gives better and smoother results. There's also SWISH. I think SWISH is the best one so far they found. And again, SWISH should look something. There's also Soft Plus, very similar to all. They're all very similar, but let me just find where SWISH is. Yeah, here is SWISH. So this is what SWISH looks like. Again, just exactly like you have seen MISH looks like. The differences are very tiny. These are just different activation functions. So it's X times sigmoid of X. And these are just different activation functions that you could use. Instead of using ReLU, you use these, and not theoretically, but practically, they give better results. So once you use them for training, you notice that the model is giving better results. And what you will notice with YOLO v4 and YOLO v5, they didn't change anything in the architecture from YOLO v3. They just added these different tips, right? So let's just continue through the config file and we will see what are the different tips that they added. It's just different ways of training and stuff like that. So again, different convolutions. Let me find the YOLO layers because these are the important layers. So this is what is really influencing us the most, the YOLO layers. So inside YOLO layers, you'll find lots of information that I do not care about. Mainly you'll find number of classes and lots of other information such as class normalization and intersection of a union normalizer. This is the name of the loss that you want to use, non-maximum suppression that you would like to use, the beta version and the max delta version, just different hyperparameters for YOLO layer. What is important is you always have the number of classes equal to the number of classes of your dataset. The next very important thing to do is make sure that the layer right before YOLO has a specific number for filters. This specific number for filters, if we go back to the lecture, is equal to the following: 3 times 4 plus 1 plus number of classes. Can somebody remind me, where did we see a similar formula during the lecture when we were speaking about YOLO V3? Especially for those who did not take the Introduction to Computer Vision course. I see that they have disappeared. For example, Lev is not here and Ozzy is here. Okay, so Ozzy, maybe you could help us. Do you remember something like this? Seeing something like this in the lecture of YOLO V4 or YOLO in general? I know you cannot speak, so you can just send me a text, or if you are not here, then maybe somebody else could answer this small question. Anybody remembers this formula?
It's something like number of filters.
Yes, let me go back to it then, right? So, right, Canva, lecture on object detection. Let's just go to the final slide, right? Final beautiful slide. Here it is. So remember the this one? Yes. So remember this last final layers. So there are 3 scales. Each one of these scales will contain the following classification or the following objects, right? So we said there are these objects. Each bounding box or each box contains the following information: 4 for bounding box classification regression, 1 for objectness score, and number of classes. This is just for classification, multiplied by 3 because we said there are different versions. There is the rectangular, there is the horizontally laying, and there is the vertically standing. And this is why we always have to set. So this is manually, you always have to do this. Always remember to change the, always change the number of filters of the convolutional layer before a YOLO layer to be the formula that we have said: 3 times 4 plus 1 plus number of classes in your data set. This is something that you always have to remember. If you just go through the whole, this rest of this article or this, what is it called, of this config file, you're going to see mostly the things that you already know. So just convolutionals. There are some up samplings, a few here and there. Up samplings. Can somebody find up samplings? Yeah, there are some up sampling in here. Stride equals to, maybe meaning we will double it. And there are these routing, meaning we will take the content of layer 85 and bring it here. So remember, routings, upsamplings, convolutionals, and the rest is just exactly what you have seen in the class. Now we go to other architectures, for example, YOLO Tiny. The main difference is instead of having 3 layers, we have only 2 scales, right? So we come here, instead of having 3 scales of object detection, we only have 2 scales of object detection, meaning it's a much smaller architecture. There are bigger architectures. So let's say, for example, this one probably has much more, 1, 2, 3, Just 3. Okay, let's go to CSP maybe. Maybe it would have a bit more. Yeah, it also has 3. So there are either 3 or 1. There is this tiny 3L, I think also has 3, 1, 2, 3, has 3, but it's still a smaller model. This is a good model also that you can use, tiny 3L. There is tiny, there is YOLO v4 normal, there is YOLO v4 new. They just added something here probably. There's YOLO v4 X Mish. Mish again is just a very beautiful activation function that you can use. And there is also Swish, which is another activation function. Now, CSP is what we have seen previously called scaled YOLO v4. We will speak about scaled YOLO v4 hopefully after we finish this lab. Oh, wait, I think we're running out of time, right? Yeah, we can do this like next week because object detection models are very important and there are lots of them. So we can spend as much time on these and as many revisions as humanly possible. So now let's come back to our in here. So what we do, we get the configs, we fix the configs for the data, and we get the pre-trained weights for those specific configs. Where do you find this information? You just go to pre-trained models. Let's come back up. Let's stay here just so we don't lose this location. And yep, let's come back up here. This is YOLO v4. Darknet. Here you will find a section for pre-trained models. So for example, you want to work with YOLO v4 P6. Here are the weights for it. You want to work for it with P5. Here are the weights for it. You want to work with CSPX Swish. Here are the weights for it. You want to work with, let's say, find me YOLO v4 Tiny. Here's YOLO v4 Tiny. You want to work with YOLO v4 Tiny. Here are the weights for it. And they tell you what is the mean average precision already, what is the speed, and all of this information. So now that we have, so now we know where to find the configs, where to find the pre-trained weights. We have already covered most of this information in the description. We've seen all of that, seen all of this. Now for the data. For the data, you need to create 2 main files called the object.names and object.data. Object.names is a very basic file. Okay, maybe somebody's in the comments. But anyway, so there is the object.names file, which is a file that contains the list of object classes, very basic file, right? And then the object.data just contains the following information. How many classes do you have? Where is the training data? Where is the validation data? And where is the object.names file? And this is just where do you want to store your different versions of the training, what is it called? Your different versions of the models. I have no idea where this voice is coming from. It looks like a sneakers voice. Sorry. Let's continue and I will investigate this later on. So let's come back now to the architecture of the data. Not here, here it is, right? So you have the location of the training data, you have the validation, training, all of this information. You create your object.data. Here it is, contains the number of classes, train, validation, location, all of that information. And if we go to data, here you will find, this is starting to bother me a little bit, this voice. Okay, so here is the location of the data sets for training. So this is just the different images used for training. If we go, for example, for valid, for example, it would be easier. Here it is. We come here, object, and you will find the image with a TXT file containing all the different classes or all the different objects in this image. First is the class category. Second will be the XY coordinates and width and height of the object. Okay, so this is just how the data set looks like. You just put the links to all of this, and that's it. Now, yes, this is how we create the data, the train TXT. So basically, we just put the list of all the images for the training, all the images for the testing, put them in a validation.txt file, and that's it. This is for creating Rust or writing the custom training config file. You can either do it manually or you can do it using code. So here, for example, they are reading the number of classes, and here they are changing all this information, such as the learning rate, number of steps, number of maximum batches. And step 1, as I said, and step 2 usually are 80% of maximum batches and 90% of maximum batches. And hopefully they are changing everything that is related to YOLO v4. Yes. So here, as you can see, any file, I'm probably assuming that they are accessing everything that is related to YOLO. Any in the YOLO layer, they will change this classes equals number of classes. So they're just changing the number of classes. Sorry. And of course, every single right line. Okay, so here, and for every single one of the things that are before YOLO layers, they are changing it, the number of filters, every convolutional, sorry. Let me drink some water. Yeah, so every convolutional layer before a YOLO layer, they change the number of filters to it in the following formula: number of classes plus 5. 5 means plus 4 plus 1 times 3, right? And we said this is how many class probabilities that we have. 4 plus 1, so 4 for bounding boxes and 1 for the objective score, multiplied by 3 because we have 3 different rotations of the objects. Sorry. Nice. So now that we have all of this done, what we usually do is simply we can just take a look, verify that everything is done correctly, and we start the training very fast. So here in the training, you will see the architecture of the model, how many weights, what is the output shape for each one of these layers, lots of information about the model itself. And here we have the training. In the training, you will see a lot of information. So for example, here, 10 hours left for the training, the next calculation of mean average precision, and all of this information is here. The rest is completely useless because really you don't need to go through it. But for to show how do we run inference on it, the inference is pretty simple. Darknet, detect, give it the config, give it where is the weights of the model you want, and what is the image you want to do inference on. Direct, very direct, right? Now for the mean average precision, it will be something very similar to these tables provided to you by YOLO before. And I think we are already going a lot after the time of the lecture. So we will stop here. I know that we have covered a lot of information. Next week, we will spend even more time on YOLO v4 and YOLO v5 and Darknet, I mean Mask RCNN and Faster RCNN, and we will build different Miro mind maps in order to just make sure that we have something that just combines all the things and all the tasks you need to remember, all the different steps you need to remember to train any of these object detectors. As you see, the code is already here for you. Once you understand how it is and understand how it's working, the changes you need to make are very minimal, but they're very important, right? So if you just make any error in any of the formulas that you need to fill in, everything will just crumble down. So it's very important to just have something that is like a step-by-step guide for you guys to explain to you how you train different versions of YOLO. So YOLO v4 Tiny, YOLO v4 CSP, and all of these architectures, we will speak about them in another time. I will not go into YOLO v5's training code. It's much simpler, but we will do it, as we said, in the next lecture, because I think we are approaching to the end. It's very simple also as it is. So the code is already here. All you need to do is just change the data source and just change a couple of configs. We will go through that in the next lecture. Do you guys have any questions about the content we have seen so far? If not, then I would just ask Anna and I think also Camille, right? Camille, yes. Anna and Camille to stick around, whereas the others, if you guys don't have any questions, I think we have finished the lecture.
Can I also stay about asking about the project?
Yeah, of course. Go ahead. Yeah, you can say. No worries. Anybody else who doesn't have any questions about their projects, you can. I know it's a lot of information, so just sleep on it. Next week, we will spend a lot more time on all of this information, and hopefully it will stick to your minds and you will be able to train any object detector in matters of seconds.
Hey, about the project, is it okay if
Yes.
I'll be first? I need to like go somewhere soon.
Yeah, of course, no worries.
If others
Do you
don't
want?
mind.
Yeah, if you want, we can create another Zoom link. If you could create a Zoom link for just the two of us, I just transferred your Zoom link from the iPad, and once we finish, I come back here and take the next person, right?
Okay, sure.
Yeah.
I'll send her in a second.
Thanks a lot. Same thing for the others. Just prepare what are the questions that you guys want. It will be very quick discussion with each person individually. If we do not have enough time, we can schedule something else for the next lectures. No worries. Maybe if Camille is not here, then
yeah, I'm here. I'm with Dima. We are from the same account.
Okay, good. Just to give you a heads up, I read your message, and it's of course I completely agree with what you have said. Definitely, if you are working as a backend developer, you're not going to need to do a lot of research and stuff like that, but you need to work with object detectors or stuff like that. So try to think of an application that is very visual, right? So what I want for you is something to show off during interviews. This is something that I've seen a lot with the previous students of this course. Usually the projects, the practical projects that they make is something that has a very beautiful GitHub, easy to read README with lots of pictures and some interactive website that they can quickly show to the interviewers, explain the code, and basically just show off their skills on both computer vision and, of course, machine learning for production. Just one small thing, try to think of an idea that is a bit more visual, right? So you gave me two ideas, and the first idea is a bit too easy, like it's a cheesy idea, like you find a lot of it, a lot of people already doing it, so it's not going to be special to brag about during an interview. And the second idea is just too complicated and too hard to build. So try to find something
perfectly balanced. Super
yes,
easy
as
and
everything could be, right? Nice. So yeah, just try to find something that is perfectly balanced, not very cheesy, not something that a lot of people already have seen, but still not very difficult for you to build. So since you are focusing mainly on the back end and front end and not focusing on the machine learning part specifically. So good luck. I'm just gonna jump with Anna right now, and we'll be back in a matter of seconds. Hey guys, so next, who is next?
No, can I be next?
Yeah, go ahead.
Oh, do we do it as a separate call or?
If you don't have any private information or maybe like a super sensitive data set or something like that, then we can just do it here. And I think Utkarsh is not going to steal your work.
We can surely do it here if you don't mind.
Yeah, let's do it here. Yeah.
Yeah, I'm doing a project with Ozzy about interior decor design, and basically what we want to do is predict the cost of design by the number of factors. This is a very abstract idea, and I thought you could give a hints about what could be a feature pack, what can we use
Okay.
as a base for our regression model. Basically,
So you're trying to predict the price of what exactly?
Of the price of the core design of a house.
Okay, so the core design of the house based on the image of the house?
Yeah, based on the image of the house, and maybe some other numbers of factors, some things we can also take into account.
Okay, okay. And how would you think this is useful? Like, where would you use this for?
Where do you think we can use this?
Yeah, I would say because like if you already have the image of the house, then the engineers have already done the estimation, right? But if somebody would say, I want something similar to this image, right? Like a client comes in and says, I want the house similar to this house, but gives you some changes such as like the size is smaller or something like that. It's very complicated. Actually, this is a very big project. Like this is a very, very heavy industrial project that would like take a year at least to work.
I don't think the aim is an industrial project, but rather something to have a hands-on and get something to learn.
Okay, do you have the data for this one?
No, but we can as well make a crawler and crawl some real estate agencies and make something out of it.
Find the price and stuff, right?
Mm-hmm.
Yeah, maybe you could do something like that.
Yeah,
and I would.
Is pretty doable.
And what?
Yeah, just doing data set sounds doable.
Okay, so doing the data set sounds very doable.
And we're pretty familiar with crawling the website, so I think it's fine.
Okay, so this is great. So you have the data. Are you going for image classification directly and image regression, I mean, or maybe you want to do some object detection and stuff like this?
That's what you wanted to ask, because we can stick to the simple option, just feed an image into the model and get a numeric output. But we can also consider another number of factors like the year, the location, geographical things.
That's amazing. This is sensor fusion. This is great. This is good. Yeah, I like that.
Maybe the content, maybe the fabric, maybe the materials.
Yeah, certainly. This is great. This is very interesting. Yeah. Go ahead. This is a very good idea. Try to do it, but make sure that you have a very beautiful interface. I want a beautiful interface, and I want beautiful code also. I really want very beautiful code. So try to use the best design patterns for what is it called? For software architecture and what is it called? For deep learning projects embedded in software.
Oh,
okay.
You think we need to build the software out of the model?
Not a software, just like a beautiful interface, just like a one-page website.
A website, huh?
Or what were you guys thinking?
I don't know. For now, we were just thinking about gathering the data and training the model. And
okay, so just focus on that. Yeah, just focus on that. After you finish, I will give you a way to build a website in 2 seconds.
Oh, that would be very nice.
Check out something called Streamlabs. Let me, not Streamlabs, Streamlit. So this is a very beautiful library for building websites in Python. Personally, I use it every job. We use it locally inside Pepsi. We used it in Provectus, all the different jobs. Whenever we have any project of computer vision or any project of machine learning, we always have some sort of a website using Streamlit that we either use locally or we just show off to clients to interact with the models, right? So Streamlit is a very simple one. Even I am horrible at web design and all of these things, and I can work with it very easily. So no worries at all.
Okay, so I guess for now we'll just try to gather data.
Yeah.
Try to think about the feature engineering, and that's going to be focused for next week or two.
Perfect. Amazing results, right? So if you want also, if you find something, if you find it a bit too difficult, because I said the data set looks pretty big, you could check any of the ideas that I've sent in practical recommendations. Remember, I always send some videos, and all of those can look like a very, can be a very good idea for you guys, right?
Yeah, but
okay.
If it gets complicated, I think you can switch the idea from not regressing the cost of the design or whatever. We can try to extract multiple features from the picture. For example,
I like this one. Yes, this one sounds a bit more realistic. Like, for example, the number of windows.
Maybe we'll reverse the task a bit and extract the materials, maybe some other features like make it one to multiple outputs, for example. Not have one
yes,
output,
I agree.
Multiple outputs. And
I agree.
Them as well.
Yeah, certainly. Find it very interesting. Yep, I agree.
Okay, I guess that's it for my questions. And thank you for your feedback. Yeah.
Thank you. Next person.
Can I?
Go ahead, yeah.
Yeah, so I have a question. Did you look at the project for introduction to computer vision, or was it Karam alone?
It was Karam alone, but can you remind me of it?
Yeah, okay. So I'd like to show you our project. We done it actually in group, but I can't share the screen. Okay, I'll just get started. So our project was not a particular research, so not a particular data set, task, model, and so on. But it was a software tool called Training Pipeline for automatization of all of that things, for creating experiments, conducting them with different models and data sets of your choice. So there's a framework called PyTorch Lightning. I think you know it. And yes. The tool we developed, it's based on PyTorch Lightning, and it's basically turns the work of like parsing data set, creating model, and so on, conducting experiments, logging everything, to just editing the YAML config.yaml file, where every field is just explained. And you run one command in shell, and model is trained, and everything is saved, what you specify. So you can specify different metrics, different what to log, in which format. You can use like TensorBoard logger, weights and biases, and so on. So for the introduction to computer vision, we implemented it for image classification. So you use any classification data set, you use any model, you train everything and save everything.
I like it.
And I wanted for this course to do the object detection in the same way. So is it good enough or what?
And add instance segmentation. If you add this one, I will give you A.
Okay. Instance segmentation, you mean the mask RCN?
Mask RCN only, yes. Only mask RCN.
Okay. Okay.
So it's not like a big task, right? So
yeah. Segmentation is far more easy than an object detection, actually.
Okay, perfect. Great job. So I fully agree on this task. It's a very good one. You have the green light.
Okay, thanks. Goodbye.
You're welcome. Next person.
Yeah, we can go.
Go ahead, yeah.
So we had an idea about the air canvas, where like you can draw the picture with the finger, and then this picture can be translated into some other things. So is this hard enough for us?
I think it's pretty hard. So basically you're saying the artist or the person can draw anything and you convert it into a real painting, right? Or to a real object. Yeah. Is that it?
Yeah, exactly.
This looks like a very interesting project, but I think it's a bit too difficult to build. Do you guys think you can do it easily?
No, I think we can, like, we have two models like Wakugan and, for example, and Clip.
Okay.
And we can take the drawing that the person made and feed it to this network with possible some textual description.
It's pre-trained.
What? Sorry.
It's pre-trained. Is it already existent, or you have to train it from scratch?
Clip is pre-trained. Bakugan is like his usual gun. It just does what usual guns do.
No, but is there a model that is trained to do this, or you have to train it from scratch?
Trained for what exactly?
I mean, for example, for let's say YOLO V4, there is a model for YOLO V4 that you can easily use, and you have the predictions. For example, generating images of faces, there is a pre-trained GAN that generates images of faces. If you want to generate images of cats, there is a pre-trained GAN.
Yeah, but in our case, we don't have a specific class of an image like a cat or a person. Just sketch of something that the person draws with his fingers, maybe put some textual description, and then we just generate it, like considering these two factors.
Do you think you can do this?
Why not?
Perfect.
We can try at least.
Yeah, you can try at least, right? I really like the idea. It sounds very, very complicated. I really love it. And I hope you guys can make
well, I think like the image won't look like something super real, but some surrealistic pictures, like usually what Bakugan produces.
Well, so anything is actually very good. As I said, it's a very complicated idea. So if you guys do anything, it will be a very good contribution, honestly. And it will be something definitely very visual. So it's easy to speak about this on your interviews, and hopefully it will land you some good jobs.
Okay, then we'll try to do it. Thanks.
Thanks.
You're welcome. Utkarsh, are you still here, or you just forgot to log out? Yeah, you just like left the mic and okay.